if you tilt the image into a height map,
Whoa.
it completely breaks your notion, your visual processing of what's going on there. It works really well, but when I do this, if I do this for about a minute and I stop, the yaw is like to the left.
He promoted for this game called The Fight. And so his like Daddy Trejo with move controllers.
Welcome everybody. Tonight with me there is Anton Mikhailov, who worked on PS Move back in the day, and he's gonna do a technical breakdown of this technology and absolute insanities that went into this to make it as small as possible so that as usable as possible for all the other game studios on PlayStation 3 to be used. And PlayStation 3 did not have high-tech hardware. And with us, there is Handmade Network lead, Ben Visness, who also dabbled in this technology, tracking technology in the past, which makes me the least knowledgeable in this domain. So I will be goofing around. That's my idea for my added value.
Perfect. Keep it entertaining, otherwise we'll rat hole into boring math.
Exactly. And we have a live simulator prepared, like online program that Anton pretty much assembled in the last couple of weeks or days to showcase some of the technical difficulties, and also stories and math and code that's related. The issues, both from the design of this thing, from the product standpoint and market standpoint, but also technical.
I joined Sony in 2007, which was like basically out of university. I had a university professor who was friends with Sony R&D, PlayStation R&D, and so I was like one of the graphics class students. This was around the era of the code that you and I reviewed, Wookash, with framework.h. So that should also, if people saw that code, will give them heebie-jeebies, because that's like the era I'm writing a lot of this code. But basically, he recommended me for an internship because, I was motivated to do all this graphics stuff. And so I end up in Sony R&D, and I'm supposed to work on physics. So I'm like a computer graphics physics person. I'm one of like 2 interns for the summer, and I'm like graduating that year. But the manager that I'm assigned to goes on vacation accidentally, like timing doesn't work out, and he's like, sorry man, like no hard feelings, whatever, just stuff didn't line up. So he's like, you guys, you're joining, you're only here for, I don't remember, like 6 weeks or 8 weeks or whatever, but he's like, I'm gonna be gone right now, and I think it's like a week or 2. And so me and this other guy are like, what do we do? He's like, read the PlayStation 3 manual and just learn about PhysX, which is the library that, like, it's the physics library. And I think his group was basically in charge of like porting it to PS3 and improving the internals and like optimizing, right? So our intern plan originally was that we're going to work on PhysX together. This guy goes on vacation, great guy. Anyway, so other intern reads the specs and starts to like noodle in the PhysX code. I read the PlayStation specs and I'm like, where are the demos? So I open an example demo. I'm like, here's a physics box falling on the ground. So I end up making like a lunar lander demo with full like joints and all this stuff. So it's like a little mini game. And so when manager comes back, he's like, what have you guys been doing? I was like, I made game. And he's like, have you been looking at the physics API? I'm like, not really, but I made game with physics API. And he's like, but anyway, he's like, cool, that's great. He wasn't like upset about it, but I was like, we're supposed to work on the internals. And in the meantime, I made friends with Richard Marks, who was also at Sony. And he was famous for making this thing called the iToy. But he's like sitting a few desks over, and he doesn't have a team at the moment. He's like, I'll show you in the timeline why it's important. So I started doing camera demos with him. So I basically just switch internships like midweek. And all of a sudden, I'm doing camera demos. I've never worked in computer vision in my life, but he's like, Rick Marks has a PhD in computer vision and like avionics. So he's like a legit rocket scientist from MIT/Stanford, PhD in computer vision. And he's like, have a camera, here's some libraries, make some demos. So I switch tracks because clearly I'm not that motivated by reading physics code. I'm instead motivated by making demos. Other guy stays on physics code, and I'm like, sweet, I'm doing demos for Rick Marks. So then I'm making a bunch of computer vision demos, and I make this demo that like does contour recognition and kind of makes game assets out of like pen curves or whatever. Rick's like, this is cool. We're presenting to Phil Harrison, who's head of like PlayStation Worldwide Studios at the time. Come with me, you can present alongside with me, right? Okay, I'm like 22 or something, right? So he just grabs me and he's like, let's go present to Phil Harrison. So like week 4 of my internship or something, I don't remember the exact timeline, but we're presenting to like a bunch of Sony people, and everyone's like, who are these people? Like, well, they all know Rick. Who's this guy or whatever? So I get to meet a bunch of people. Internship ends, they're like, we want to hire you full time. I'm like, sweet, what do I work on? He's like, you can work with Rick. I'm like, all right, great.
Well,
so I join.
On whatever Rick is doing.
Basically. So I basically
amazing.
get assigned to Rick. And so here I'll kind of like bust out the timeline of how it's going to go down. So I'll screen share.
Can I also interrupt with one question?
Yeah.
I need to know your emotional state when you are joining as an intern. Do you think about, oh, I need to prove myself so that they offer me a full-time position after 6 weeks? And then you're like, if that's your mindset, mid-internship you decide to switch teams? Like,
I did not have that mindset. I honestly, in retrospect, I was thinking about this last night as I was writing the outline. I was like, this is bananas. I didn't think about any of this, right? And so the other context is I've been like a PC gamer my whole life. I've literally never owned a console up until that point. Like, I grew up in Russia, had like handmade PCs. My dad made a PC, all this stuff, right? Never had a console. My parents were like, console too expensive, like not worth your money kind of thing, right? You get a computer, you can do work things also.
Math.
So yeah, so I'm like, I'm coming in and I'm like, yeah, PlayStation's kind of cool, whatever. Like PCs are where it's at, but like, whatever, it's interesting internship, right? So I have like zero kind of like, it's not that I don't have respect or understand. I just have no understanding of like the magnitude of the people I'm working with or whatever, like all these console legends. I'm like, I have no idea who these people are. No grounding whatsoever. So I'm just like, these people are cool. I'm trying to just do a good job. So it's not that I wasn't like, I was cocky or something. It's just like, oh, that's cool. Let's do some fun things together.
Special kind of fearless.
So, yeah, like it must have appeared as a really bizarre form of confidence or something. But like in retrospect, I just had no idea, right? So I was just there. And so my plan was like, well, okay, I have nothing to do for a week, like with the physics day. I'm like, well, presumably when my manager comes back, I want to show something good. So I'm like, what's the best thing I can show? I'm like, I think if I show a game, that'll be pretty good. And, he was really cool. He was happy about it. So it worked, right? So I think that was like my first indoctrination of understanding that if you make a demo, it like turns out well for you. So I basically continued that on through my PlayStation career. It's like, if I show a demo, people are happy. Like, so just make a demo somehow. So we don't have to deal with timeline, but basically what happens at that point is Phil Harrison that summer or that year or whatever, I looked up this chronology because I was actually curious. So he transitioned out of Worldwide Studios head, and Shuhei Yoshida came in, who is like famous in all PlayStation circles, but he was head of Worldwide Studios for years and years. So here's me, I'm joining here, 2007, right? So like I went to school like somewhere here, I don't know, I'm bad with time, but I finish up here and join the intern right here. PlayStation 3 releases here, so like pretty much right before I join, and also the Wii releases at the same time, and about a year before Xbox 360 releases. So now, if you weren't like following consoles in that era, this is like prime time console wars stuff. I don't know if you guys are like familiar with this kind of thing, but everyone's like duking it out, right? And if people know their history, PlayStation 3 is not doing particularly well. PlayStation 2, which was like way back here, did phenomenally. Like it's, I think either the best selling console or like very close to it, sold like 150 or 60 million units. PlayStation 3 having a rough start. Eventually it does okay, but like having a rough start. Xbox 360 is taking like all the hardcore gamer people, and the Wii comes around and takes like all the younger gamers, right? So PlayStation 3 is like not on track, let's say. And basically, you can imagine from up high, people are like, hey, we need to like address this, right? So obviously, the Worldwide Studios team is trying to battle with the 360, but the Wii is like an unknown thing. We're like, what's going on with this, right? No one really knows how to compete exactly, except they're like, wait, we have this thing called iToy, and this is the thing Rick Marks made released in 2002. So iToy is a camera. I can see if I can find like an image or something, just so people are aware. So yeah, this is the PlayStation 2 iToy. So it's like a little webcam, and it goes on the top of your computer, and you can effectively, you kind of move your arms, kind of like the Kinect, right? And there was even a game called iToy Kinetic, like literally right before Xbox 360 launched. So Rick made this thing. Very few people knew about it, which is strange because it sold as almost as many units as Gran Turismo 3, which is like the best-selling game on PlayStation 2. I think it was like 10 million units of iToy sold. But because it's in this completely unknown market, which is like kids, no one knows about it, but it sold a ton of units. And then the Wii comes around and starts selling a ton of units, and Sony's like, what's going on? Why is he selling so many units? And Rick's like, guys, we are selling units.
We are selling.
We are also selling those units for PlayStation 2. So they're like, okay. Everyone time out. So I'll stop sharing so I can get you guys back on screen. So they're like, okay. With that context, Shuhei Yoshida is like, guys, we need to bring this technology back, right? And Rick Marks is the right guy to do it. I'm not the right guy to do it. Rick Marks is, because he's well known. He sold 10 million units, and he's got a PhD. But Rick's like, okay, we'll evaluate technology. So Rick gets given the task as being like kind of the only person in the company, I mean, other than the game developers, who knows this space. He's like, compete with the Wii, basically, Rick. Save us, right? Kind of is the vibe. So we, and we're in R&D, so a bunch of companies constantly come to us and they're like, here's some tracking technology, here's this technology, here's graphics technology, whatever, right? So we're constantly evaluating stuff. So Rick has a bunch of contacts. And so people show up and they're like, here's a magnetic tracking technology, here's an ultrasonic tracking technology, here's, whatever, right? All these, he worked with PrimeSense, which eventually became the Kinect. So all these tracking technologies Rick is like aware of, and he's like, okay, intern Anton, evaluate all these things and tell me what the problems are, right? So I just grab all these trackers and I sit in a room and I'm like, well, this one has these problems, this one has these problems, this one, we kind of go through all of them. And later on, like when Mike Abrash does like Vive and stuff, he does a similar, he has a good talk about this, like why all the different tracking technologies have problems except for like light computer vision kinds of things, because everything bends and whatever. So that's like side tangent number one. We could talk about later if people are curious. TLDR, Rick is like basically tasked in a couple of weeks to present to Shuhei and all these other studio heads in this giant meeting as part of a bunch of other meetings, like, what do we do? What's our play here? So we evaluate all this stuff, sit around, and I'm like, all of these have problems. They all have issues. I don't know how any of these, like, they're all more accurate, because we're told, like, it's got to be better than the Wii. Like, it can't just be, like, throw an accelerometer in. It's going to look stupid that we just copied them. We can't just copy them. Plus, we're not copying them. We have, like, Rick Marks, creator of the iToy from 10 years ago. Like, we got to be able to do better. All right. So I'm like, all of these are bad, though. And he's like, okay, well, we had this technology back in the day, which I'll try to find a picture of, which basically was a ball on a stick. And so the technology was Rick put a foam ball on the top of a stick. This is from a YouTube video you can find online. So it's a green ball on the end of a controller, I think, strapped to this PlayStation 2 camera footage plus like JPEG compression. So the idea is that it's just a green ball. You could see it's about the size of his fist or like bigger, right? And that camera is 320 by 240. So anyway, like no resolution. So he's like, I got this library that tracks a green ball. It tracks any color ball. But basically you take this ball, you put it in the middle of the screen, you press a button, the camera looks at the pixels of the ball, and then it's like, it's green. I'm going to track green from now on. And then you can wave it around and cast magic spells and stuff like that. They never shipped it for PlayStation 2. So he's like, that we have that, but it can't ship. And I'm like, why can't it ship, Rick? And he's like, well, problem is the lighting. Lighting is like really rough. And this is, okay, remember this is 2007. This is before deep learning, any of this stuff. Like the state of computer vision is like, Ben probably knows at that time. So
y'all are overestimating my computer vision.
well, you
expertise.
said you did robotic sense. Yeah, just
Well,
pull it apart. No, you got it. But I mean, you kind of know what I'm talking about. Back then, there was like the idea of tracking something was like research stuff. It wasn't, you can't just like whip out your phone and be like, track a human or like no AR, QR code tracking, kind of like all that stuff came much later. So you didn't really see this stuff outside of like military applications or motion capture or sometimes film or whatever. So Rick being computer vision PhD who happens to be at PlayStation, he's like, I can track this glowing ball or just foam ball, right? And he's like, well, the problems are, one, the ball's giant. Nobody wants to hold a giant ball. Problem two, there's lighting. Lighting means, if there's different lighting conditions, you might kind of calibrate it close to the camera, then you step back and the lighting, like even as I move back, the lighting changes. So you'd move back and the ball would lose tracking. So all the demos he'd have to do, he'd kind of have to be in a pretty controlled lighting environment, stay close, right? Problem number three is colors. If you ship this thing, right, let's say it's a green sword or whatever, well, what if someone has like a yellow or green object in the background? Now those conflict. You can't ship a static thing, right? So he's like, so it doesn't really work. And rotation, you can't really get rotation because it's a sphere, right? So it looks the same. We use a sphere because it looks the same in every direction. But if you use a cube, then the lighting becomes even more of a problem because of the different So he's like, it's hard, but you have this library. And I was like, what if we make it an LED? At least that solves the lighting problem. And he's like, yeah, we sort of tried it, but then you still have the same problem with color, right? Because lighting and stuff like what if we make an RGB LED? And he's like, why? I was like, well, then we can change the color. I'm just literally spitballing like on the fly. I'm like, what about that? And he's like, okay, that's interesting. Maybe we should try that. So I was like, okay. I go home that evening and I drive to Home Depot, which is like the hardware shop. And my degree is in electrical engineering and computer science. So I can do enough electrical engineering to like put something like this together. So I don't think the processor is in there. It's like a tiny little Arduino chip. So I put this thing together and it's a PVC pipe. I go to an electronics shop and I get this like switch that becomes the trigger and then a button. I Dremel all this stuff together. There's an RGB LED inside. And I wire like a controller into it. This slot here is for an inertial measurement unit. So I lost it. I don't know where it is, but you basically put like a little accelerometer and gyroscope in there. So, but it wasn't there originally. So I made this glowing wall and I bring it in. I'm like, check this thing out. Let's try to calibrate it. And it works. And the new camera is higher resolution. The old iToy for PS2 was like 320 by 240. The PlayStation 3 one is a whopping 640 by 480 pixels, which gives you, just enough pixels to be able to, you'll see what that actually looks like. But basically he's like, great, make a demo. So I take his code, which is, my modus operandi, which is like, make the demo. So I take his code for tracking this green ball and I find an accelerometer online, like a little package. And so I stick it on the end, and the accelerometer just gives you, acceleration, and the gyroscope gives you rotation of something, or like the rotation of velocity. I throw something quick together to integrate the gyro to get rotation, just enough to get it off the ground that I can calibrate it, it zeroes it, and then I can move it, and then the rotation is tracked by the inertial measurement unit, and the position is tracked by the sphere. And the sphere can now be smaller because, well, we don't need to get any position from it. It's also glowing, so it means it's like a brighter signal than this, it's not affected by lighting. You can play in a pitch black room, totally works. In fact, it works better. he's like, okay, this is pretty sensible. You know, these other companies that just show this magnetic tracking technology, ultrasonic tracking technology, it all has problems. And I mean, he saw it. He sort of double checked my work. But this thing could work. Okay, demo time. Like, Sony CEOs arrive and they're like, all right, what do you got? What's our play here? And Rick's like, we're going to do that thing. So we would like go through the presentation. We're like, all these things have problems. This is our solution. And everyone's like, what?
Was this the actual thing you hold, or was this a different
this was
one?
literally the thing that I probably
Did it
demoed
look
with.
like
We had
this?
two of
Like
these,
a
the other
tape-
ones
tape?
at Sony.
Did it look like this, like a tape, like a ball
yeah.
tape? It's like this is what will save us. Like this is what will save our
This
product.
is what we're doing. But so that's why I sort of told this story, because like it gives you a sense for how we were operating at the time. Like, it wasn't PlayStation was like, we need to acquire someone. It was like, who in our company can solve this problem? It's Rick. Rick solved the problem. Full delegation, autonomy mode over the entire product branch, one person. And then Rick's like, got some ideas? I'm like, yep. And so we get the ideas and we pitch it. Right now, obviously, we did do our due diligence, so we're not fully cowboying it, but the amount of like immediate autonomy dumped on us was like immense in retrospect, right? And maybe I don't know the reasons for this. Obviously I don't represent Sony or anything, but probably the fact that PlayStation 3 wasn't doing super hot didn't mean we had like money in the coffers to like go and acquire companies, and we also had to act quickly because the Wii literally launched already and it was already eating PlayStation's lunch, right? So it was like, gotta get it done now. And also the optics of it, like if we use our own technology, it makes us look better, frankly, just like, and we do have a lineage of it. Rick did this thing, sold a bunch of units, like it's a good PR story as well. And so, and keep it all in the family kind of vibe. So I think that's all those things roughly contributed. So did you have a...
Can I ask a couple, like, slight tangent on some of the other tracking stuff? I mean, you say, like, the only thing that works is light. I mean, that's what the Wii does, right? Yes. They have, like, infrared emitters in the sensor bar, and then it's just looking for those. I mean, was that not on the table, or is it just too similar to what Nintendo was doing to seem like a viable product decision?
So the PR side of it, definitely, yes. Like, if we just literally ripped it off, it's just not, I mean, come on, like that's not how we roll. We're cooler than that. But on a purely technical ground, the problem with that method in general is that you've got two lights that are on the, it's got the light bar, and I think the spacing's like, I don't know, 6 inches, 7 inches or something. And you're looking at the light bar with the camera. Now the Wii's tracking, again, 2007, it's inside the remote. So there's an infrared camera, but it's inside like literally a remote. The kind of chip you can put on a controller back then is nothing. So all it's really able to do, I think it was custom silicon that would find the dots and just get you the 2 XY locations of the dots, kind of barely, right? And, it had issues with lighting as well a little bit. But the point is, mathematically, if you get the position of 2 dots from a camera position, when you rotate, they move, which is what tells you that it's pointing. But if the dots move with respect to the camera, you can't tell if it's because the controller moved and therefore the camera moved, or the controller rotated. You simply can't tell. Right,
because looking from off to the side would be the same as looking from far away or something.
Now, if you knew the size and the spacing of the dots, I think you might be able to back work something, but the dots are so small and the processing is so, limited that just wasn't the case. So the Wii could only detect pointing rotation, and the original Wii only had an accelerometer, and, that was for the waving. So it kind of was like a 2-mode device. It was like you can point, and that was like for the shooting and pointing games, or you can wave it to do kind of different sort of stuff. And so we were like, we want full 6-degree freedom tracking. I don't know why we said that, but I think this was after the fact. We're like, I think we can, so that's going to be our goal. But originally we're like, well, why don't we just do something like that in reverse? Because like Rick's demo was kind of that in reverse. Plus, the new thing we had is that Rick was able to put characters and effects over the camera feed. So it was like augmented reality. So I was like, okay, our play is going to be augmented reality with tracking. That's going to be the vibe. And it was already proven to work on PS2. Kids loved it. And you can do body gestural games or you can do sword games. Seems pretty good. But let's kick it up a notch and do rotation too, because to overlay objects well, you really need the rotation of the object. And all of Rick's demos were position only. So like a character can kind of only float above the ball. And if you rotate it, it would sort of stay in the air kind of thing. Yeah. So that was,
Sure.
And you had another one?
Well, the only other question, I guess, is just like scale of 1 to 10, how bad were the like magnetic and ultrasonic and tracking stuff at the time? Because I randomly had a friend who was into a lot of like the experimental input things, and he like it was just like my friend's older brother, but he was just like hoarding this tech wherever he could find it, and he got these like Razer Hydra controllers that, as I understand, it's a magnetic tracking thing, but it would have been, I think, a good bit after the magnetic tracking that you would have been evaluating at the time, and it was terrible from what I remember. Like he had made some game where you could like fly a spaceship, and it barely worked. It basically didn't work, and this was a product that Razer was shipping.
Right. So Razer is a product that Razer is, how do I state this without violating things? That may or may not, the technology behind that product may or may not be some of the technology that we evaluated. Because Razer didn't make that thing. They bought the technology that other people didn't buy. But generally speaking, magnetic technology has a fundamental problem, which is that so Razer's technology, not Razer's technology, the name of the actual company that makes that eludes me, like the actual, you can look it up on Wikipedia or whatever. That's an active magnetic tracking technology. So there's like an emitter, and the base station, like the little ball, is emitting a field, and then the controllers are sensing that field. And so the basic idea is like you emit a 3D field, and the controller has a magnetometer inside, which detects the orientation of the field. I'm probably butchering it. The internal tech's more complicated, but you can imagine that if you have a 3D field that you know, and inside that field, you kind of can like sense things. You can sense proximity and orientation. You can figure it out. This technology is actually originated from the military. They used it in tracking purposes for military headsets. It was used for flight simulators in like army simulators. So it's good stuff. It's only good at a very short range. So if you have the tracker quite close to where you're tracking, and you can put the tracker where you want, and also if you can calibrate the environment. So even in a plane, there's a lot of magnetic interference going on, but you can calibrate it because you know it's that one plane and you're going to be in that plane. The problem is in a user's home, anything that's metal distorts that magnetic field. And so the problem with that technology is that every time we tried it, they would have to do a full calibration of the environment. And so just from a user experience perspective, it was just vetoed in the sense that it worked when it was set up, but no one until we worked with it saw the setup. Like they would demo it, and then people would be like, oh, this is really good. And we're like, can we see the full bring up? And they're like, oh, we'll need a couple hours in this office. And we're like, no, like out of the box, like what is this going to look like? And we're like, user's not going to be walking around their room clicking and checking a magnetic field map. And again, to their point, it's like they're not game developers, so to them this might have seemed like a minor problem. But I mean, imagine opening a box and being like, calibrate your room. It's like people don't even like calibrating the Vive lighthouses or whatever, right? And that's barely anything compared to this. So that was the problem with magnetics. And actually, this will be like foreshadowing for other magnetic technologies we attempted to use in the Move as well. But magnetics basically are a headache that's probably not worth it. Ultrasonics are a different problem. So ultrasonics work by chirping ultrasonic sounds, and then you listen to the return signal. And so the basic idea is that, you want the controller to be small, and so you have a microphone on the controller, and you have 2 or more emitters of these ultrasonic chirps. And just like akin to a GPS, you try to triangulate the chirps. So you try to listen to the chirps coming in and then figure out its position from there. The problem there is what's called multipath, and it's basically sound bouncing off the walls and coming back into the controller from a different direction. So if something bounces, it takes like, double the distance or more to get to where it's at. And so all of a sudden the controller gets a reading. It's like twice as far, twice as close, twice as far. And like you have to reject those. And so the company that was doing that had an accelerometer and gyro inside. So it was like, oh, if the reading comes really far, then I'm going to reject it. But it just didn't really hold up. And again, we throw it into actual users' living rooms and like mirrors would really mess with it. So again, just putting it under load, it was like really problematic. So
sure.
So that was kind of, we didn't feel like we could ship it. And I think it's, history sort of has validated that. Like no one has actually successfully shipped like a large scale magnetic or ultrasonic tracker since then. And everything that's been shipped is vision-based in one form or another. Even the lighthouses are, light-based, even though that's sort of, now people are switching from it to inside-out tracking. But again, it's now you can put enough processing power on the inside to do these.
That's future talk. That's future talk.
Future talk. Yeah, so we do this demo, and so again, Rick and I get carted out in front of all these execs. And at this point, we just have my 2 or 3 weeks worth of code, right? Which is like Rick's algorithm for tracking spheres. I adapted it to track a glowing sphere slightly. I'm not even sure I changed any of the algorithm. And then I added the inertial measurement unit, put it together, put a sword on the end, be like, look, there's a sword. It's an augmented reality. Here's the thing. And I show it, we show it, everyone goes, okay, great, this is pretty good. One guy in the back of the room raises his hand, goes, your math doesn't work. Can you please, like something to the effect of, can you please stop lying to the room? There's no way this could be tracking properly and this is not going to work. And I was like, well, luckily we ran the math. And I was like, no, the math checks out. It's just deadpan. The guy in the back of the room turns out to be Mark Cerny, who is like architect of the PlayStation 4 and like console legend extraordinaire. Super duper smart guy. The only guy in the room who's like live notepadding the math that we're discussing and then arrives at a different conclusion because he sort of makes a naive assumption because he's not in the field. But I like call him out. I'm like, you're thinking of the naive version, and yes, you're correct about the naive version, but the non-naive version actually works to better.
You're too naive.
Like, okay, well,
you said you're too naive to Mark Cerny? Wow.
Something like, I mean, I didn't mean he was naive. I'm just saying that the basic version behaves as he's describing, but Rick is smarter than that. And so I like kind of leaned on Rick a little bit. But again, I have no context for who these people are. And if
fearlessness again.
There's just like zero fear. I'm like, no, it works. It's fine. So he's like, let's talk in the break. So, I sit down with him. Again, I have no idea who he is. And I back of the napkin just show him like, no, the math is going to work. And he's like, cool. And then we were friends from there on. Like, so when we worked on PlayStation 4, it was fine. Like we're all, so I didn't mind the forwardness and he didn't mind the math. So like, it was great. It was a great relationship from then on. So that's kind of like the origin story. And then it kind of got more, not greenlit, so to speak, because it's more to that. But then basically everyone's like, yep, we'll do that then. And you guys are doing it. And so now it's me and Rick to do the move controller. And then we leave that meeting saying, all right, how do we actually ship this thing? And this is like 2007, a couple of months after I started work. So then it's like, okay, on paper, you can kind of imagine how the whole thing works. So let me sort of, at this point, unless we have any questions about that section, that's like section 1. And now we're going to talk about like, how do you actually, what's the math of the tracking, right? And like, how does this set up?
I think it was a great introduction, I must say. Mm-hmm. I ran one quick poll. I ran on YouTube. It was only 5 voters. But I asked, were Rick and Anton given too much authority? Because I can't imagine running a company and having like products selling in millions and be like, hey, you, save the company now, stat. I can't imagine this. So
What did they say?
the poll was unanimous. It was no. They were given just enough
Good.
authority.
That's the correct answer.
Thank you, everyone. So I'll share really quickly. I guess I'll just jump into screen share at this point, and you guys should do first. But here's for people that are not familiar with what the PlayStation Eye looks like. That's this camera over here. I might have like a better image of it. There. So that's the camera. It's kind of got a funky design. And that is because it was designed by a computer vision person, not sort of an industrial designer.
It's kind of got a unibrow.
It's got a unibrow. And the reason it has a unibrow is because this is a microphone array, not super common at the time. But this is what allows you to do basically noise cancellation. So if you want to do teleconferencing, because, okay, remember, this is console stuff. So we're sitting right now, my camera is like an arm's length away or something. In the console world, people are sitting on a couch at least 2 meters away typically. So between 1.5 to 3 meters away. And it varies in the world because Americans have huge TVs and they sit far. In Japan, the rooms are smaller, TVs are smaller, people sit closer. So there's a big range of how people operate. And the camera has this really long barrel in order to have low distortion. And it also has 2 field of view settings. So you can actually click the lens, and it has a narrow mode and a wide mode. And the narrow mode is for video conferencing. The wide mode is for playing games because you can like zoom in. Anyway, that's the basic idea. So you've got this camera and it's sitting on top of your TV, just like my camera is sitting on the top of this. And eventually, you end up, just in case people haven't seen how this actually works, where's the actual like gameplay looks something like this, right? You're going to have a camera, you're going to have some controllers, and then you're like punching stuff or swords or shooting or whatever, right? So the camera is all the way over here, person's over here, and you need a fair bit amount of space because you're going to be swinging your arms around wildly. Okay, so, whoa, that's crazy. All right, like that. So the diagram for that is something like this. Like, it's looking from the side view. We have the TV, and we're going to draw our camera, right? So it has some field of view, and it's usually kind of tilted down a little bit, but that doesn't matter for this. And somewhere out here, probably around 2 meters away, is going to be a controller with the sphere on it. And I'm going to put it actually over here just to make the drawing a little bit easier. Well, we'll see. Again, I didn't rehearse this, so you guys just pause me where it makes sense. So the camera has a field of view, and that field of view is I think 73 degrees, something like that, vertically. Anyway, whatever, something like that, 50, 60. I have the actual numbers. We'll run the numbers in a second. And so basically, when you image this thing, you're kind of imaging. Well, you're really imaging at some imaging plane, but you can imagine sort of like the controller gets imaged like this, and the sphere, which tends to be pink for reasons you'll find out soon enough, is some portion of this image, right? So in the image, you'll see like a couple of pixels, right? So let's see, maybe it's like 10 pixels, right? And so the entire frame is 640 by 480. At 60 hertz. So it's a fast frame rate camera, at least for that time. Back then, webcams were like 15 frames per second because we designed it for tracking. So you're looking at something that's like, a part of your image, and it the basic idea is like, it's obvious that from the position, kind of the XY position within the image, that you can get the XY position in the room. But what's maybe less obvious is that, well, if the controller's really close, well, now, I mean, it's obvious if you think about it, but now it's going to be like 100 pixels, right? Because if it's closer together. And then also when you move a little bit close up, like you could see it from my hand, if I'm moving just slightly, I'm probably moving like, 5 centimeters or something. I'm moving across the entirety of the image. Whereas if I'm back here, I move slightly, I'm only moving a little bit. So already you kind of know, okay, the Z distance is going to have to play into where the position is. If you're only trying to overlay something over the sphere, then you just need to find the position and maybe the size. But what we were trying to do is like boxing games and stuff like that, which means we need to know the actual 3D position of the controller relative to the camera.
At some point, can I try and guess what a bunch of the like problems would be? Because like my understanding of the problem is pretty naive, but like, so I mean, is now an okay time to just throw a bunch of random
let's do it. Let's do it for fun.
So
you write them down and then we'll see if we'll cover them.
Yeah. So I mean, the stuff that I've done in the past is basically a threshold on like the hue, saturation value, something, or RGB or what have you, right? You have to like pick out which pixels are good and which pixels are bad. And all I've ever done is like a binary threshold, whereas like you get down to a black and white image. I suspect this is the Mark Cerny, part of the Mark Cerny, like this will never work sort of
You're
problem.
already getting the vibes. You're like, this will never work.
Yeah. Well, so that's one thing. It's just like how if you only get down to a black and white binary, like it's a controller pixel or a room pixel, then at any sort of distance it's going to be really crunchy. It's going to be only able to move in very distinct increments. And the best you could maybe get is like the sort of rounding in a sense of like, maybe the average, right? The center of the ball as you perceive is sort of
true danger,
stepping along by half of it. But it's still pretty bad. Also exposure, like does the ball get blown out so that it's just white? Does it like, how do you actually know that whatever colors you're seeing correspond to the controller and make sure that the thing is adjusting the exposure so that it actually sees the controller reliably, or adjusting the brightness of the ball or something. Motion blur. Like if you're punching, if you're waving it around, like even at 60 hertz, like especially if the exposure has to be higher because you're in a dark room or something, there's no way that you have a ball anymore, right? Like how do you and I don't know, is it a rolling shutter camera? This is like something that I'm just barely so then if you're going side to side, then the thing's probably like shearing in some horrible way. Like
and more.
I don't know if I have any other naive objections at the moment, but these are all I mean, at least in this case you don't have to find the corners of something, which is one of the pitfalls that I ran into. So my only expertise with this, like it was sort of hyped at the beginning that I've dabbled in this. Well, it's only in the context of high school robotics, which I'm repping the shirt for my team.
Hell yeah.
Go Fighting Calculators. But basically it was just like, whoever's making the competition throws some software at us that's like, here's a little thing for making OpenCV pipeline. And the process is always like threshold your image, find the corners, average the corner positions or something, and call it a day.
That was sort of, I wouldn't say state of the art, but that was par for the course back then. OpenCV was like it's like handmade mentality circa 2027. Everyone's like, just import OpenCV and we're on PlayStation. It's too slow. It's all on CPU. PlayStation 3 has to be on SPUs. There's no OpenCV code that runs on SPUs. Only Rick's code runs on SPUs because only Rick is the computer vision guy at Sony. So we couldn't use OpenCV. I mean, we could, but in practice, most of that stuff was too slow. So But
even that aside, it's still basically just like very simple full image sort of processes. And, like finding edges and finding corners it was always like this really terrible, broken sort of process. And we were never able to get very good signal out of it, except a rough estimate for like the center of the target, which is fine if all you're doing is trying to point your robot at the goal before you shoot a ball or something. But, it would be nowhere near the precision that you need for what you're talking about. And I don't have the, Cerny napkin math for exactly how bad it is, but my gut says no way.
The math is missing.
That was a perfect.
But all the problems are probably like the Mark Cerny problem list from the back in the day.
I think this was pretty much the best tee up I can hope for, because the thing we're going to jump into now is like actually doing the back of the napkin on how bad it's going to be. So before we do it, just for the sake of other people who might not be familiar, I'll just do this really quickly and hand wave. If people are more interested, we can do the math. I can explain the math more carefully. But basically, we need to know the distance of this thing to compute the XY. So there's something like, let's call the image space coordinates something like UV, because they're, in image plane, but we need to know the XYZ. So we need to somehow go from UV and radius to X, Y, and Z in the world space. And the way you can do that is if you sort of make this triangle, you have this angle and you have like the size of your ball. And so you can basically, again, hand waving, figure out the relative, not angles really, you figure out the relative size of this versus like if you project through like the inverse projection onto the other side. Basically, you figure out the focal length of the camera or the field of view, the sensor size, and you can work out a formula that gives you something where the z coordinate is proportional to 1 over radius, right? And there's a bunch of constants in here. But effectively, this makes intuitive sense. The smaller the radius gets, the farther away you are. And
it falls off like the asymptotic thing that you'd expect, where the size changes. The size sort of shrinks slower and slower as the ball gets farther and farther away. So you actually like lose precision kind of the farther out you go.
Yeah, we're on the same wavelength. This is great. And so the XY position is something like the UV coordinate, something like times Z, right? Perspective, projection kinds of stuff, right? Again, hand waving. So your XY mostly depends on your XY position, but it also depends a little bit on your Z position. And your Z position crucially depends on the radius. And this is the thing that Mark immediately spotted. He's like, this is going to be, a disaster train wreck, because this radius, as you're saying, everybody's saying, can't be worked out because of all of this, right? Luckily, I'm completely naive to any of these problems, as in like how hard they are, because I've never done computer vision ever. So I'm like, well, I mean, Rick reckons we can do a pretty good job, so let's try it. So back at the napkin math, bring out our calculator. Okay.
Can we increase the font? Is this the version?
Oh, yes. Look at that.
Nice.
Saved by my code. Relying on handmade code midstream. Okay. Okay, so for people not familiar with not code, it's just basically simple. But so this is just like two radians function from degrees. Okay, so you have the FOV of the camera. The actual diagonal FOV of the camera is like 73 degrees, but when you work out the vertical FOV, it works out to be about 47. Again, I'll save you the gory details. It's just a bunch of tangents and whatever. The radius of the ball, so the actual controller, the sphere is 45 millimeters across in the final version. Okay, but we can play with this. And then, so that's the diameter. And so you divide it by 2 to get the radius. So 45 divided by 2, that's going to be your radius. The other thing you need is, we talked about, basically you're talking about half angles here, half the field of view. So you're also dealing with half of the resolution. The half, half the resolution is 480 divided by 2. So it's the full resolution of the camera divided by 2. And this is your S scaling factor here. So it's the radius in millimeters times the half resolution of y divided by the tangent of the FOV divided by 2 to radian. So you can work this out as basic, kind of like high school trig. Exercise left to the user.
Of course.
Can you at least like draw out the triangle that
Sure.
you're working with here? Like tangent of what exactly? Oh, really?
A cleaner drawing would look something like this. So you have this would be the forget the terms, but basically if your lens is, you have a pinhole lens model. So this is the pinhole lens of the camera. Field of view goes out like this. This angle here is 73. The half angle here is the 47 angle. Behind the imaging plane, I'll draw it a little bit smaller. Here's the sensor. So this is the imaging sensor. And here the things you care about is like sensor pixels and sensor millimeters. So you need to know the millimeters size of your sensor. You need to know your, well, in this case you don't. You can also, you can do it a bunch of different ways. Some people do it via focal length, which is like the length of the distance to the camera to the lens to the sensor. And so out here somewhere is your sphere. And you take, what you're looking at is the ratio of the known size of the ball to the pixels versus like the ratio of the full width of the sensor versus the known millimeter quantity. The way I'm doing it in this particular calculator version, I'm working off of the field of view instead of the focal length. And so tangent, half field of view. So tangent is going to be opposite over adjacent. So tan O over A is going to be this quantity here. And so that is a ratio between like either half of the sensor pixels or half of the height of the whole sensor, or a ratio of like how small this is versus like a ball over here. Because right, like the ball when it's farther away or closer is gonna look, it's gonna sort of proportionally shrink using this thing. So yeah, these are basically the triangles you can draw and you can work through it. So, but you know your known quantities. Okay. Assume that you know the field of view of the camera. Assume that you know the radius, the true radius in 3D of the ball, and you know your sensor resolution. If you have those things and you know the pixel radius of your ball, you can work out the real world z coordinate from that. So if we do that, this is the formula if you want to check your work. So this is your radius in pixels. So this is the formula, right? So we're using the formula below here. So distance of radius pixels is this S factor divided by the radius in pixels. Okay. So the first thing we'll look at is just, we'll comment those out. Okay. So these are in meters. So in millimeters, 243, right? So let's do some naive math. Be like, how big is the ball when how close is the ball when it's like 100 pixels? Which feels like, okay, 100 pixels is a good amount of pixels to work with. At 100 pixels, the ball is 121 millimeters away, which is like a centimeter from the lens. So that's not going to work. So you can reverse the formula and actually work out, you can do it this way. Pix of distance, z, is just the reverse of that, right? So z.
Red pixels divided by S.
Z divided by S, right? Well, and then inverted, right?
Because Z is the radius pixels.
Yeah. Things like that.
Yeah, that makes sense. Or wait, no, sorry. The distance is in millimeters and you're getting into...
Oh, yeah. Okay, pixels. Yeah, whatever. Yeah. Anyway, we're not going to mess with it. Basically, we can just fudge it until we get the value. Let's imagine we want to play at like 2 meters, right? 10 pixels, 1.2 meters away, okay? 9 pixels? 6 pixels? Okay, so 6 pixels is what you're looking at when you want to be 2 meters away. And this is the reason it's like increasing now quite rapidly. So like this is at 2.2 meters. If it was 5.9 pixels, 5.5 pixels, it's already at 2.2 meters. So this is like, I'll show easily what Ben was already freaking out mentally about. 1 over r, if you plot, 1 over x, we all know 1 over x looks like this. And this goes to infinity, right? And then this goes to infinity. Well, I forget what the bound is, but basically as it goes. So imagine what's happening here. So we know we're talking about 1 over r, right? So here we have 1 over r. And then here we have z. So, this is r. And
z is 1 over r.
Z is equal to 1 over r, right? There we go. So if we're over here and radius changes by a little bit, z changes roughly by the same amount, right? Because the slope is roughly 1 here. But if we're out here and radius changes by the same little bit, the z is now changing by a very different amount, right? And you can flip it the other way. And so what this tells you is that when basically small changes in the radius cause a big changes in z when you're far away. And when you're close, frankly, it doesn't matter, because to play this game reliably, like, look, I'm on this camera, I need to see both my hands. So if you just figure out the mathematics of this space, my wingspan is probably, I don't know, like 1.5 meters or something. You need to be something like 2 meters away from the camera to fit me on the screen to be able to play. And usually you want to have 2 people to play because these are party games, right? And I'm playing alone, forever alone style. We want people side by side. So you need to be at least like 2 meters away to be able to do any kind of party game. And at 2 meters, you're now saying, okay, if I have an error of like, half a pixel or whatever, it's not looking good. So here you can play with this value. So let's remove this. Imagine this. So this is, imagine we're at 6 pixels. So it's 2 meters away. So that's printing this first value, and then comma. The next value we're going to print is the distance of that plus like minus the noise and plus the noise. So imagine you have, a tenth of a pixel noise, right, in your answer. Let's say you misestimated. Let's do it by 1 pixel, because this is Ben's initial worries. Like, these are binary pixels. You decided whether the ball is a ball or not. If you're off by a pixel, what happens? So distance minus half of that plus half of that, spread it over that distance. If you're off by a single pixel, you're off by 34 centimeters. So 34 centimeters, which for non-metric users, Wookash knows how much this is 30 centimeters. Okay, so if you're off by 1 pixel in your radius measurement at 2 meters, your z distance is changing by this much, right? And so you can imagine that if you're playing the game and you're looking at this controller, and I'm like boxing or whatever, if I'm off by half a pixel, my hand's now here. And then if I move over, now it's here. This is the level.
Well, and I'd expect it to be continually doing that. Like that, it's just constantly, thanks to the noise and the signal, it thinks your hand is moving forward and backward over this crazy range.
Right. And so if we came into that presentation and we were like, yeah, but we'll smooth it with an accelerometer, Mark would have ate us alive. But luckily, we thought about it like a little bit more than that. But as you'll see, maybe not enough, because all these things also come up. And we weren't woefully ignorant of them, but let's just say we were highly optimistic about them in that respect. So let's run the code now, and I can show you guys what. Does this show up pretty well? So.
Yeah. I think
this is the simulator I
guess
wrote.
Wookash should tell me. He knows what it looks like on screen.
It's always better if you can increase the font, but I'm assuming it's...
This font, I can increase the font in the code, but it's going to mess up. Can you read the stuff? Is it readable?
It's it's gonna.
Even that's not super readable for me because it's that Dear Mgui pixel font.
I can bump the font, but it might screw some of the stuff up. If it's readable, I'll narrate it, but I can also bump the font. Let me see.
Let's
have
try
to do it live.
Since we're gonna spend some time with the simulator, we can try bumping the font.
You want to just try it out?
Yep.
Then we can try to...
If it's gonna
You
be a
wanna bump it?
disaster, then we go back. Because there's compression and there's like issues.
Let's hope for the best. Might have to just retune some of the... it'll work fine. How's that?
Nice.
Pretty good? Good job, I'm Gooey. Live on stream. That's what I'm talking about. All right. Okay. So this is sort of what everyone expects you'll get, right? And then if you zoom in, you can see the pixels, right? But as we just discussed, that's what it looks like when you're 25 centimeters away. Very rapidly, as you move to 1 meter, this is kind of what you're working with. This is like your best case. You're never going to be closer than 1 meter. Realistically, you're going to be more like here. This is at 2 meters. In America, you're going to be here. And I actually implemented the simple algorithm in the shader because it's 2026 and you can just do it in the shader. So what Ben is basically saying is, if you look at the hue, red for everybody. If you convert the image to hue space, you'll see, black just gets converted to red, but whatever. You see this is all nice and purple. And you can also do the chroma of it, etc. But effectively what that algorithm is like in hue space, take the angle and then threshold it. And so if you're within that angle, color the pixels. So I'm coloring them white. We can change the highlight color.
But excuse me. You said earlier on that it's supposed to be 6 pixels. And now we're like at least triple the amount of pixels in width, right?
Right. Well, we're not at 3 meters.
And was that 6 pixels the radius before? Because you were doing all the math with...
6 was for
that pixels
the radius?
was the radius, and that was for 2 meters.
Okay.
Now, what you're seeing here is the aperture. If you remove the aperture, which now I'm going to have to reset real quick just so here, if you play with the aperture, this is the blur. So I did like a quick ray marcher and do like a thin lens simulation. So if you have perfect focus, then it's exactly that. I mean, you can zoom in, you can count 1, 2, 3, 4, 5, give or take. Right?
Okay.
But because you have some aperture, it's not perfectly in focus. Spoiler alert, that's going to turn out to be very important in multiple ways.
I didn't even think of that on my list of objections.
Yeah. But no one thinks about the aperture. But yeah, let's see. So we'll put it at 2 for now because that's like a comfortable working distance to work through this stuff. Okay. So if you sort of track it, you get something like this, right? And because of camera noise and et cetera, it's not perfect, right? You're not going to get a perfect silhouette. And this is what Ben's talking about. Now, naively, what a lot of people do is they take the bounding box of this object. And then you take the bounding box and you say, okay, well, now I have a width and a height, but I know it's a sphere, so maybe I'll average the two. Maybe I'll get like half a pixel of happiness from that because it's an average. Maybe I average some noise or whatever. If you do that, it turns out that you do get about, a 1 pixel level worth of accuracy, maybe half if you're lucky. But Rick had a better idea. Rick was like, we know it's a circle, so why don't we take the full area of this object, and we know the area of a circle, which is, pi r squared. If we divide it by pi and take the square root, we get the radius. What's the advantage of that? Well, now you're using all the pixels, not just the pixels at the edges. You're using these guys too, the ones that are at the distance. And if you do that, when you move forward in and out, you can see maybe the side pixels wouldn't have changed at all, like the bounding box wouldn't have changed, but there are fewer pixels and there are more pixels appearing. So even though I'm changing the distance and the bounding box isn't changing, our Z value would change. This was the level of technology we had for that demo, and this is what Rick used to do for his demos. The math for how accurate this is like discontinuous because it's pixels and stuff. But I think we worked it out that you get about 1/4 of a pixel accuracy in the best case, meaning like you have no noise, like you get all the ball pixels because no lighting, we were like hoping the ball's brightly lit. 1/4 of a pixel accuracy. So if you plug that back into here, you say...
And that's for the center position?
No, for the radius.
Sorry,
yeah.
I gotcha.
So, because basically the math is, you have some...
Oh, yeah, because that's the quantity you're trying to find. I guess you all, yeah.
The XY position...
The X and Y, I suppose that's easy. You can do the bounding box.
Yeah, the bounding box
take
the center. And it turns out for the XY position also, you can take like the weighted sum. You just sum up all the pixels and divide, and you get like the centroid. And it's a little bit more, it's more accurate than the bounding box. So then the fully naive version is the bounding box, and it's woefully not good enough. But Rick's version was take the area of this thing. And so if we have this thing and let's say it's 6 pixels across, and we worked out that the noise is about 1/4 of a pixel, well, we're getting closer. We now have 8 centimeters of Z noise, which, goes from something like that to something like that. So still pretty unusable, especially at 2 meters. But you start to get into a realm of like, okay, maybe we can throw the accelerometer data into it. In the back of our minds, we're always like, at some point, we're going to give up on the vision improvements and throw the accelerometer and gyros at it. And hopefully that smooths out the rest of the noise, right? But that's the hope.
The addition of accelerometer means that from frame to frame you have acceleration, so you kind of have a better prediction of where the X and Y will be, right?
Yeah, so that's a good point. So basically, accelerometer gives you the acceleration of the body. And so what you see is like what Ben's saying is that there's noise. The computer vision signal is saying, hey, you're jumping forward and back by like 8 centimeters. But your acceleration is not consistent with that. Your acceleration is saying you're barely moving. And so you do what's called sensor fusion on those signals, and you say, okay, let's trust both of you guys a little bit in some form. And in this case, we just end up trusting the accelerometer a lot more and saying, look, vision, you're on crack. Like, you can't be doing this kind of jumpy. XY, yeah, pretty consistent. But the Z, no, throw it out. Now, you can actually just stop there and just sensor fuse the signals. And a good filter will even detect kind of like the variance of your signal and just start trusting the accelerometer a lot more. But it's not free lunch because integrating accelerometers, you would think that it would just work because it's like, okay, well, we know from like physics that if you integrate acceleration, you get velocity. If you integrate velocity, you get position. So you think, oh, I have an accelerometer. I'll integrate it twice and I'll have the position. It'll all be beautiful. The problem is there's noise in the acceleration. And when you integrate noise, it adds up. And then when you integrate it into velocity, you integrate it again. So you're integrating noise twice, and your error in position grows quadratically. So even if you're just holding it still, tiny amounts of noise means your whole thing drifts away. So if you trust the accelerometers too much, they make you fly away, basically yeet off the camera. But if you trust the vision too much, the whole thing is too noisy. So you have to find some kind of balance. And so the better your vision is, the more you can use accelerometers for a shorter amount of time. Okay, so we look at this, and we could talk about more like how to do the sensor fusion later, because it'll show up, but we also need to get the rotation purely from that. Okay, so we come back from that meeting, we're like, okay, we know we can do 1/4 of a pixel, and that got us in the door. But Rick had the suspicion that we can do better. And I'm like, sure, let's try. If we look at the ball, his point was, okay, well, look, we're thresholding this thing. And like Ben said, can't we do something not binary here? Can't we as I nudge this a little bit, look at it go. Like, it's doing all sorts of subpixel stuff, right? Like it's not really just changing immediately. And look at the distance. When I'm changing the distance, look at all that data. There's lots of data in there. Tons of data, like 3 pixels worth of blurry stuff. Can't we do something with it? And so that's it, just vibes. And then he's like, he's been thinking about it, but he doesn't, he hasn't had time to think about it. And he says, if we work it out, if we get the noise down to 1/10 of a pixel, now we're looking at something like 3 centimeters, which is this much. And with 3 centimeters, you can probably just throw the accelerometers at it and it will kind of hold its own. And if you can get to better than that, like I think we can ship this, right? Because it's got to be better than the Wii, but the Wii doesn't do the position or anything. So if we can get position to this level, not bad for 2007. So he basically, like my job for the next, until shipping, is like get it from 1/4 to 1/10 of a pixel. Okay. Before we launch into that, I'll add a couple of complexities, as Ben mentioned. This is the best case. This is like in a dark room against a black background. So let us now slowly walk through the pain to which I arrived once the honeymoon period is over. So first off, the ball is not uniform because there's some kind of shading to it. So the environment light, the sphere is not evenly illuminated, but that's a separate problem. The problem is that you have some lighting on the ball. So the ball is going to have some kind of like, light component coming in from the outside. That's actually what you get from detection because of the light, right? If you don't have any light, it's like, oh yeah, beautiful, you nailed it. As soon as you start having light, maybe, right? And you could see this part is like barely pink. And what Ben was talking about is if you get your exposure wrong, now your exposure is like, actually that looks like it's working better, but because the hue, I know why. Yeah, it's the light color. If you change the light color slightly, it's like, oh, now you can lose the whole ball, right? So
because that changes the hue of
the ball.
Yeah.
So basically, I'll bring the exposure back down to a sensible amount. So quickly we realize, okay, exposure has to be really correct, otherwise it's going to blow out the whole ball. And also we have to do something about the lighting because the lighting is not uniform, and without it, we're getting less than the pixels we bargained for. So now all of a sudden, the other problem with the area fitting method, as you can see here, once the lighting is turned on, not just the accuracy is 1/4 of a pixel, here it's literally giving you the wrong answer because the actual radius is like somewhere in the middle of these blurry pixels, like the blur is sort of going like this. But the answer it's giving you is this center. It's because it's thresholded. So, maybe that's acceptable. We don't need to know the true Z. It's just relative. But anyway, that becomes an issue. Okay. So that's the first problem. The second problem is your background is never really purely black, right? Let's assume your background is like something like this. Like a nice gray wall, like in the back of this office. That's looking a little worse. And we're already at 2 meters. If it gets farther, it gets worser. But then you can't really have no noise. Really, there's noise. So I don't know how bad the noise looks on stream, but
It's bad.
yeah, that's about right. That's about how it looks. So there's noise, right? And it actually looks better under motion than if you look at a single frame. So if you pause a single frame, this is what the computer's actually dealing with, right? It's not dealing with these kinds of temporally average things. It's dealing with this single frame at a time kind of thing. On top of that noise, let's see if we could just pull back a little bit. So you're in this sea of kind of noise, and you don't actually, you don't have a fixed background. You actually have some kind of other background. So
Nice.
Here I took a photo of literally my room so we can throw it in there and see what it would look like in this actual situation. So we'll put it like somewhere here where it's interesting and zoom back in, follow the sphere. Okay, so you're looking at something more like this, where you've now got a variable background. You might it might be partially on one background and another. So you don't necessarily have a constant background. And actually, I think maybe this is a problem Ben also knows about, but maybe didn't think of the back of his mind. But cameras are not actually RGB. They're what's called a Bayer pattern. And a Bayer pattern means that each pixel doesn't just have a full RGB color. It has a red, green, or a blue color. And because cameras have so many pixels nowadays, you don't really notice this. It's just like kind of like CRT monitor, like a monitor, right? But a monitor in reverse. You have red, green, and blue things, and they combine. So that looks like this. So actually, your signal, if you look at it, there's more greens than blues or reds. And that's because our eye is more sensitive to green. And so the way that they make the Bayer masks, they just put more greens in there because typically for luminance, that's what matters the most. So they just shove a bunch of greens in there.
Is this still true?
Yes. Yeah.
What?
This is still the case. But now we use like neural debayering and all this stuff. So it's like, and the pixels are tiny and the algorithms to debayer the image are, amazing, and they take context into account, et cetera. But to my knowledge, everything is still Bayer patterned. There's like, yeah.
To clarify one thing though, can you toggle the Bayer thing? So it looks like the size of these Bayer colored squares agrees with the size of the like pixels.
No, not yet, because I haven't turned on what it actually looks like. This is what it would look like if you had a good, there used to be a Foveon sensor, which actually had an RGB triplet. When you have a Bayer camera, it actually looks like that. So when you actually get the Bayer image and then debayer it, which is the process of reconstructing the RGB from this half resolution signal, it actually looks like this. Now there's better debayering algorithms, for sure, things with higher contrast, but running it on a PlayStation 3 in 2007 is not necessarily an option. For one, actually the camera had an onboard debayer, but it introduced random artifacts because it was visually tuned, right? It's meant to look good, not track well. Mm-hmm. And so you're then trading like better quality debayering for random things, which, as we've discussed, if you're off by a half of a pixel, you're in the trash. So we can't have bayering introducing anything. So we'd rather work with a crappier, low resolution image than with a beautiful debayer. So this is actually closer to where we're at the end of like a camera simulation. So you are going from something, that doesn't have Bayer, doesn't have noise, doesn't have all these things, to something like that. Now, the other thing you also get, well, we'll get to this later, but there's different kinds of noise and different kinds of gain issues. We'll get to that in a minute. But this is the basic set of constraints. So anything we want to throw in, Ben, from anything else you foresee after seeing the basic start of it?
I think this is already... I only vaguely knew about Bayer filter things. I just knew that there were like 2 greens for every red or blue hand wave. That's about all I know about it. So, but it is unsettling to me how familiar this sort of thing looks now, having zoomed in on a lot of photos and trying to understand why my photos look like crap.
Yeah.
So,
yeah.
I want to interject for a moment. And
yes.
Now you're presenting this, Anton, as if it's like, hey, here is a list of problems.
Yeah.
When you were doing this, it wasn't like that. You needed to discover them. And I'm assuming that you did not do like a super fancy simulator with all of them included. It was a trial and error. Like, how did this journey look like to find out these problems and not to be thrown off track during the development?
So the way it, I actually did end up writing a simulator later. I'll talk about that. It wasn't nearly as good as this, ironically, and I wrote this thing in like an afternoon. Software these days is like phenomenal. And also I know more things. I was just winging it. But basically it comes from like Rick squinting at it and being like, it's moving more, like there's more data than I've got, and I reckon I can get to a tenth. So then I just go back to my desk and I zoom on the image and I start moving the ball a little bit and being like, what's changing here? Like, what's going on? And freeze framing. But there's an interesting thing to mention there. Is like traditionally the way computer vision is done, later I found out in those days, is that you get a recording from a camera of like a sequence of what you're trying to track. So maybe it's like a vehicle or a person or whatever. And a researcher takes that sequence and they pass it to like OpenCV or something, or, you know, their code plus OpenCV. It runs all the frames, it prints out the data, you look at the noise. It's very much like a testing procedure. You have your test sequences and you're going in this very experimental, scientific, rigorous way where you're like, because you're usually working with an academic advisor or something and you're saying, okay, here's my test data. There's usually known test suites. You know, there's like test data sets of like, oh, you know, here's like, you probably know this from medical field, there's probably medical computer vision test data sets, like find these cells or whatever. So the way that world works is very different than how I was working because I wasn't part of that world. I did not have any tools. So I was like, I can start the PlayStation and look at the video. And then I'm like, what can I write from there? Okay, let's freeze the frame. Let's look at some freeze frames. The bandwidth wasn't that great. And like the raw images were large. So it was like hard to put a lot of them into memory. So each of these images is 300K. You could put a bunch of them, but not like, so anyway, I guess what I'm trying to say is I never recorded sequences, like pretty much until the end of development. And so the way I learned about it is just by every day, I just start the thing and it would be a new day and it would be new lighting conditions. And it would be like a new, the guy behind my desk has a new shirt on and I'm like, oh, I guess green's a problem. Tomorrow it's like, I guess blue's also a problem. So I'm getting this stochastic sampling daily of like, what kind of things show up in my camera? And that's kind of how I'm treating it. And so pros of that approach is that I'm sampling a wide variety of things that might happen. And I'm like paying attention because somebody shows up, they've got like a work badge and it's got like a metal bit and that's glinting and it's creating pink pixels in the bottom right corner because it's super bright and the debayer makes it purple. And I'm like, oh, I guess small shiny things when debayered introduce purple noise. Like now that's a thing I know. Whereas if you had a test sequence, you'd be like, you may or may not know. And if you're running the same test sequence, you just don't encounter new things. The downside is no day is the same. So yesterday it might work really well and today just doesn't. And so I'm like, did it never work well? Like, is it gaslighting me? But I think in the end, this was kind of the right way to do it for a consumer product because it's kind of keeping you honest. Like if it just works worse today, you thought you were going to work on something, but really you're working on figuring out why it's worse today because you're about to do a demo and you're like, hey, Rick, I figured it out. And that's like, didn't work anymore. So for a long time, I had this pattern where I'd stay late and I'd like work, 8 or 9 till 8 or 9 or whatever. And things would just work really well at night because there'd be no lighting. And I'd be like, I did great. I'm a freaking rock star. It's working so awesome. I can't wait to show Rick in the morning. Everyone's going to be so happy. I show up in the morning and it's like, doesn't work at all. I'm like, I don't have a demo anymore. And I'm like, sad face. In retrospect, it's good because you get to leave work really happy and you arrive and you're like, okay, I got some problems to solve. If it like didn't work at the end of the day, that would be terrible. You go home, you're like, oh, I got to sleep. Instead, I'd go to bed happy every day thinking I'm awesome. But actually, it's just the lighting's really awesome at night. And I figured this out several months later, like, cause I was like, it's really working. And so that's how I figured all these things out. Is I'm like, okay, pause. What changed, right? And then I started recording single image frames and be like, okay, here's a nighttime image, here's a daytime image, and I had some recordings. But because I started that way, I kind of noticed that that's helpful. And so most of the development, I didn't do any kind of like automated stuff. It was always kind of live. So yeah, that's sort of.
And this simulator, when did you got to building a simulator?
I will get to that later because it's an interesting story beat because it relates to like the craziest bug I've ever had to track down to the point where I had to write a simulator to track it down. This is literally the most bananas. It's the best bug ever, I think, for me. Okay, so that's like end of section 3. We're like now in section 4. And section 4 is like, how do we actually figure this out? How do we go beyond the binary pixel boundary, basically? Because if we can't figure that out, then we're hosed. Like this, it's not good enough. So back to screen share. So I'll show you a thing, which Rick showed me, not as a live demo, but as a thing. And I'll just show you this image. One of the worst things about computer vision is that it looks way easier than it seems. Like there's a sort of folk story where like a computer vision like a professor in computer science assigns the task of computer vision to a graduate student for the summer, and then it goes on vacation. He's like, expects it to be solved. This was like in the 50s or something. It's like, you just figure out where like all the objects are, what the shape of everything is, like back or reverse the scene, and then we'll do the interesting stuff after. And that like spawns the field of computer vision, because this poor graduate student just fails miserably. Like, and so everybody coming in, they're like, well, there's the ball. The ball's right there. Ball's there. We can figure it out. But what's happening is your brain is doing so much of the heavy lifting, you're not even realizing that none of this information that you're seeing is in the data at all. You have to like reconstruct all of it. So the cool trick that Rick showed me is that if you tilt the image into a height map, it completely breaks your notion, your visual processing of what's going on there. So if I showed you this image, especially if I didn't colorize it, you would have no idea this is a room, right? Now from context, you know that's the ball, but how do you know that's not the ball? Or maybe that's the ball. Maybe that's the ball. Who knows? So
okay, what happened with when the height map, meaning
so the height of the value
intensity, light intensity
is the intensity. It's the intensity of the light, because that's what the computer's seeing. It's seeing a value for every pixel, 0 to 255 in this case, sometimes more. And so really what you have is a pile of numbers that are scalar values. There's no structural information whatsoever. There's no ideas of circles or boxes. It's just a pile of numbers. And the computer sees a pile of numbers. There's nothing else in there. And so when you're thresholding, you know, you're in hue space, but effectively you're chopping these hills in various places. So for example, we could look at the red channel. The red channel looks like this. This is the green channel, looks a little bit different. This is the blue channel. And so things that are dark will look like holes. So you can kind of see like here, this cup in the corner just sort of looks like a hole. By the way, you can, if you look at just the blue channel, you can see the bare zippering artifacts really clearly. See how bad the blue channel is because it's half resolution from the green. See the zippering kind of here? You see it really well in the post.
Okay.
If you look at the green channel, not nearly as much zippering, right? Because we have double the pixels. But in the green channel or the red channel, equally bad. So the red and blue channel, way worse than the green. So that already sort of starts to hint to you why you might not want the sphere of a pure color. You don't really want a blue sphere, even though PlayStation wants to be blue because PlayStation's blue. Blue channel is actually the worst channel, happens to have the worst noise, etc. So that's not going to go well with PR. But basically, yeah, so when you tilt it, these are the values, right? And when you're moving this object, it's looking like that. So it's sort of like moving this hill around. And so your job is to basically find this hill using, finding it with, by color is easy because it's like, well, it's the pink one. Now, if it wasn't the pink one, for example, if it was blue, and if it was light blue, like now it's gone. So you can't just pick any color. Like now this is really hard to find. Look very much like that peak or that peak or that peak. But this is a cool trick if you want to play with computer vision. It's like that at least cures your sense of like, oh God, why can't I make it work? I must be completely stupid. It's like, no, you're not actually completely stupid. It's just a mess.
It's just
so
a disaster.
So once I got that, I was like, okay, you have to stop trying to like rush to the solution thinking, I just got to do this. You got to just accept that this is going to be a mess and that you're going to have to do something clever with the small pixel. So at this point, I started reading some papers. So I'll show some of those just for reference. This is like the papers of the time. So I found this one, 6DoF circle tracking. And I'm like, brilliant. This is what I need. From Berkeley, no less. Like I went to Berkeley. Oh no, it's Derek Bradley. Never mind. Not from Berkeley. Nothing about visions from Berkeley. Anyway, but you see images like this in the paper. I think this is like 2000 something. You're like, how to track a ball. And you see this and you're like, thanks. That's the ball I have. That's not the ball I have, man. It's huge. That is a huge ball. We can't do anything. And of course, it's like, so isolate the ball.
Ideal lighting condition. Like you can see
ideal
like
lighting
super
conditions.
light
It's
background and dark.
Yeah, and look, it's got colored spheres. Like, bro, if I had this many pixels, bro, come on. Okay, and no shade on this guy. It's like it's actually a good paper, but it's like you start to get dejected because you're like, what is academia thinking? Like they're sitting next to the camera, right? And okay, fine. So I'm like, all right. So I start looking at like broader papers. This is a welding paper for detecting quality of welds on like machinery. And now you start like when you get to industrial applications, you're like, oh yeah, these are pretty crappy. This is good. I need this kind of stuff. So I start looking at these sorts of things. I find the original Canny paper from Canny Edge Detection. I don't understand most of it. I don't have a PhD in computer vision. I could ask Rick, but Rick's like, yeah, it's Gaussians and things. And I'm like, I don't have the knowledge to understand like what's actually happening, but I'm like, okay, seems like there's these shapes, right? The profiles are not step functions. So this is like the key insight. When you have a little bit of blur on the edges, that blur we're seeing is the blur from what's called the point spread function of a camera. And so you might have an ideal box signal coming in, like it's either ball or not ball, but after you put it through a blur, the whole thing kind of blurs out. And so these blur side pixels are convolved with what's called the point spread function. So I'm like, okay, maybe there's something to that. And then I find like, I think these are army papers. That's probably a tank. But I'm like, okay, these guys are working with something like what I'm doing. They have like 8 pixels. They're trying to track.
You can count the pixels. Yeah.
You can count the pixels. Like, okay. And then I found some astronomy papers. Same thing. Spheres of 8 pixels. Got to get like really accurate. Is it 3 light years away or 3 billion light years? Like, gotta know. So I'm like, okay, we're probably going to be doing something with circle fitting. We're going to fit some circles. And then I find this one, I'm like, yes, this is what I have. This is literally what I have. Like dipole. And then, he's doing some stuff and I'm like, okay, this is interesting. I'm not sure if I found this before or after the method I come up with, but certainly this is like at the same time. He's got the same mouse that I have too. So I'm like, okay, this is starting.
Gamer.
This is called right. Gamer mouse. But still, look at the size of these spheres, man. These are huge. These are huge. And look, he's not tracking it to sub-pixel accuracy. So it's purely like what Ben's describing. You threshold the image and then you're done. But this idea of like casting rays, I'm like, okay, that's kind of interesting. Let's bag that because what that lets you do is deal with occlusions, which is another thing that will kind of come up later. Anyway, this kind of thing, perusing it, just to give you a sense of like where, state of the art is at that point. Okay, so then I get the idea. I'm like, okay, let's look at what these curves actually look like. So I plot the pixels that are actually around the sphere. And that shows me something interesting. I'm like, okay, so actually I can see this curve and it's not a step. And when I'm moving the ball, look at that.
But is this intensity? Is this the same thing from the height map?
Intensity.
But like the row, a selected row.
It's just that's right. So this is a selected row across the ball. And now I'm like, okay, if I move a little bit, look how sensitive it is. Look at all these pixels moving. I'm like, there's some signal in here. Rick was right. So, and I move in Z distance. Look, it kind of does this. I'm like, oh yeah, plenty of data. Plenty of data. We're going to get this done. So my idea ends up being, again, I don't remember if the dipole paper, I read it first or later, but it's not a, it's not a genius idea by any stretch. Is I'm like, okay, we're going to use Rick's algorithm to find the center of the ball. That's going to give us an initial guess. Once we have the initial guess, we're going to also use the initial radius guess to kind of get the inside of the sphere, like where's the starting point. And then from there,
and that's just the area of the circle thing for computing.
Yeah, that's right. So you compute the radius, so you get an estimate of the radius, because that way, at least, quick sidebar, PlayStation had like 256 megs of RAM. We talked to the game developers at that meeting, and they said for us to use it in a game, they were already super memory bound. So they're like, for us to use this in a game, it has to be like less than 2 megabytes, probably. It has to be less than 2 megabytes of memory. We need our textures, man. And the PlayStation did not have a strong CPU, like that generation. Xbox 360 had a similar issue, but it had like originally 8 SPUs, eventually 6 or 7 or something. I forget the exact count. SPUs were these like really fast DSP-like processors, but they were really hard to use. And so the developers are like, don't touch our CPU. We have no CPU to spare. Like, it's already bad and it's hard. But the SPUs, you can have like a whole SPU if you want, because we can barely use these things. Most of them are sitting unutilized a lot of the time. Later on, they got really good at programming them, and that's why later PlayStation games got way better, PlayStation 3 games. But at the time, they were like, you can have an SPU. And Rick, having written the vision code, he's like, all my stuff runs on SPU. We're like, great, we're going to put this on SPU. So we had to fit the whole algorithm into 1.5 meg of memory plus change. And just for reference, each 640 by 480 image is 330K or thereabouts. So think of it like this. Image comes in from the camera, it's 300 kilobytes. You basically mem copy it from the camera driver. That's 300 kilobytes. It's a bare image, so it's one value per pixel. We want to debayer it to do some work. You debayer into an RGB, that's 900 kilobytes. That's your 1.2 megabytes right there. So you've debayered the image.
You're
That's
done.
all you have done
At
so
this point,
far.
you're done.
You're done. So now we start to get clever. Well, we don't need the Bayer image anymore. So that's a buffer we can reuse. So Rick's area fit algorithm runs into the Bayer image. So we use the debayered set of images, run Rick's algorithm into the Bayer run. And then we basically ping pong buffers for the rest of the pipeline to make it fit. So in the end, it fits into that amount. So we're doing this as a 2-stage. The reason I mentioned that is because imagine you were really close. If I tried to do this like sweep along the rays kind of thing across all these pixels, it would be brutally slow. But what I realized interestingly is that it's only the pixels at the edge where we're going to have to do the work. I mean, it seems obvious, right? But that's what the initial area fit estimate lets you do. It says, okay, well, this thing's pretty big, so start at least out here. There's an interesting insight there, which is a bit more mind-blowing than it would seem a little bit, which is that all of these pixels just don't matter. Only the edge matters. So you think at first like, oh, I'm going to get more and more area pixels is going to give me more and more accuracy, but it just gives you like an offset. So actually, none of this matters. All of the work is just on these edges. I mean, provided you can find the edges. If you can find the edges another way, you don't even need the interior pixels. So that's like interesting insight number one. Interesting insight number two turns out to be that, oh, by the way, if you actually unstick the noise, it looks more like that. It was like a jiggly mess. But we'll keep it paused for now. And look, anyway, talk about Bayer later. But it turns out that so basically I sit down and I'm like, what is this blur amount? Because we have a fixed camera. We know this camera. It's the same. All of them are the same. So I basically go, and at one of these evenings when it's dark, I take it and I reverse engineer what's called the point spread function of the camera. So I think I have like an actual image of that, because I remember taking it because I was like happy about it. So this is like my office at night, and I've got this light on it, and basically that, you could, you can validate what the sphere actually looks like. I mean, this image is no good, but yeah, stuff like that. I mean, that's tracked already. So, but you could see this is like the real image that you're dealing with. And so I take the ball and I look at one single pixel and I sweep the ball across that pixel. I get a big ass ruler out, and I'm from 3 meters away, I'm moving the ball 1 millimeter at a time and taking a picture every time. And I basically sweep a single pixel with the edge of the ball. So instead of looking at an image, I basically move the ball through that place. And what that draws me is the sigmoid curve that looks like the edge. And I do it on a pure black background. And so in practice, what this does is gives you the point spread function. It gives you like the shape of the curve of an ideal edge passing through a pixel. And it turns out
And this is with the camera as perfectly focused as you can get it, I imagine?
It turns out that it doesn't vary that much because the PlayStation Eye has that long barrel. So it actually has a really wide depth of field. So, but it does vary, but I just did it at 2.5 meters or something. So I'm like, we're not going to do this for multiple distance. I was just trying stuff that night. And I was like, what is this shape? Turns out the shape is a pretty clear sigmoid. So actually in this case, it's not exactly right, but it's close. But it's very nice sigmoid shape. This kind of like S curve shape. And it's about 6 pixels across. So it's like 6 points along that. So I'll draw in case it's not obvious. So like, you get like your actual, your room. Like if you imagine looking at that image from the side, you have your room, and then you have your ball, and then you have your room. These are like the values, right? And the actual image you get is something like this. So you have the edge crossing will be at the middle of that point. And then there'll be a flat bit, and again, edge crossing and continuing. So your actual true edge is right here, and it's aligned with roughly the center of the sigmoid. But if you actually look at the pixels, there's a pixel here, pixel here, pixel here, pixel here, right? Something like that. And that's what that image is showing in the simulator. And it turns out that you get about 6 samples along this sigmoid, more or less. And what's interesting about that is you only need like 3 samples to fit a sigmoid. I forget. But if you know the width of the sigmoid, all you need is the height and the low part, and then you're just literally linear least squares fitting a sigmoid to a set of samples. And the kind of mind-blowing penny drop moment was like, you can actually reconstruct to an infinite resolution the position of that edge. If you truly know those samples, if you have more than 3, you're golden. You can get whatever signal. So the intuition that if you move it a little bit, your eye, you can, I remember staring at this, I'm like, I can see tiny changes, right? I can move it a tiny amount, a millimeter left and right. I can see a difference. So if there's a difference in there, I ought to be able to find it. So what's going on, right? And so that intuition is confirmed. If you have a perfect image, with no noise, you can reconstruct the position and radius of this ball to in theory, to an infinite amount, because you just fit the shape. Actually, what's interesting, what's blocking you is not the resolution. What's blocking you is your bit depth. So these are all 8-bit. So that kind of blew my mind. So like, because these are 8-bit samples, you literally only have quantized amounts of information. But if you had like 10-bit samples, you actually get better signal. If you had floating point samples, you can reconstruct this to like sub-millimeter accuracy. Now, okay, this is just theory for a perfect ball, but yeah.
But to go from the graph that you drew to what we're seeing here, you're saying sort of like, you've got a thing that's imperfectly sigmoid shaped, but you try to I guess what the height of the sigmoid will be, because you know what color you expect to see or something. And then you just try to fit that curve as best you can, and you're just looking for the horizontal position where the line crosses the middle in between the bottom and top, and that's the
you just fit it
horizontal
and again
position
you
of
use
that edge.
I won't sort of jump into a bunch of the gory details, but you because we have a rough estimate of where it is, we can use all these pixels as a guide of how high the inside is. And because we know everything that's not this is the image, we look a certain band beyond this at the surrounding background. So when we're doing this kind of like almost ray casting method, similar to this sphere dipole thing, we cast rays in every direction. And because of that, we can deal with background changes. So in this direction, the background is brown. So we know the floor is brown, but the center is purple. In this direction, it's gray. So we can calibrate the sigmoid for every direction as we do it.
Oh, I see. Because the actual luminance or whatever space you're in, so you just step out a distance that you're like, I'm confident this is not
confidence, a strong word, but I'm hoping it ain't the sphere.
You step out far enough from your center estimate to say this is probably the background, and probably it's not such a noisy background that I'll be wildly wrong.
Yep.
So I suppose if you were doing this in front of a staticky TV or something, that could be like
or
a really bad case where it has no idea what the baseline color value is to fit a sigmoid to.
A window.
But right.
God.
Leaves.
My arch nemesis.
I see.
Leaves.
I see.
Leaves. And I don't think I see it here, but here, let me zoom out. I mean, at this exposure, nothing, but at high exposure, oh God, window frames. Here, I'll hide this.
Okay, right.
Oh God, there, like, that's not a happy bowl.
Yeah.
So here, you're clutching at straws. So in this case, what would happen is you'd get some rays off to the side, you'd get some rays that succeed there, but these rays would just be gone, blown out. So now it goes to the next point. I got these rays. I'm really happy. I'm like, this is fantastic. But now like the true demon soul starts here, because now we have to figure out which rays are actually working, which rays aren't. Here, we have to throw these out. This is a case of occlusion. The other thing to remember is the ball also the controller has a handle. So here's handle on. And the handle is always trying to be all up in your business. Right?
Yeah.
So the handle is often occluding the ball too. And so you're dealing, especially when people are doing this kind of thing and they're moving so you're dealing with occlusion all the time. So I shoot a bunch of rays, and in practice I shoot like 24 rays, because there's no point shooting more because you cover every single pixel in the image. It turns out you can shoot more rays when you're closer, but you don't need them when you're closer because the ball's good and you're not concerned. So in practice, I shoot 24 rays. So similar, this person looks like 12 or something, or maybe 12. I shoot 24. I cover the entire ball because I'm trying to use every freaking last pixel. And then there's another paper which, talks about rejection, right? And the typical technique in rejection is called RANSAC, which is random sampling and consensus, which I learned like from Rick with every other vision thing I end up learning. He's like, use RANSAC. I'm like, okay. And so the way RANSAC works is it just says, look, I'll draw it out. You have this, you now have this ball, and you've sampled some points along it, and you've got a bunch of samples, but this part of the ball is occluded. Like maybe it's occluded, or maybe some stuff is there, whatever. One of these points is like, you still get an edge point. You don't know that it's wrong, but you get this, right? So we have the initial area fit estimate, which looks like something like this. We cast our rays, and then one of our rays lands here. I'm only going to draw 8 rays but we're actually in practice casting 24. And so this ray ends up being in the wrong place. Again, we don't know this. What Ransack says is, okay, for every 3 points that define a circle, for example, this one, and this one, fit a circle that fits into those points. You're like, okay, that's a circle. And then this point, that's a circle. And then this point, that's a circle.
That's
so
smart.
you see what ends up happening is that some of the circles don't look like the other circles. And so what you get is a whole list, of like X, Y, and radius for each one of these. And some of these are like, 0, 0, 8, and there's a bunch of 8, 8, 8, and one of them's like 3, and this one's like more 8s, 3. And so you're like, okay, bro, you're out. This one not right. And so Ransack, the reason they call it Ransack is because you have a lot of permutations. So if you have 24 points, so it's 24 choose 3. I don't remember, but there's like some factorials in there. Somebody can work out. There's a lot, like 2,000 or something. And so the way random sampling consensus works is you say, well, we're going to randomly sample these. We don't need to sample all of them. That's too much. Why would you do that, right? Because you usually have a lot of points, even more than 24. But we don't have a lot of points, but we do have a lot of CPU cycles, so I just sample all of them. So I look at every single point in brute force.
Nice.
Because I don't want to miss anything. So we just brute force.
So you did non-random sampling and consensus? Okay.
I just did brute force consensus sampling. And so that improves.
24 choose 24 or something to this.
I don't know what it is.
No,
24
that
choose
wouldn't be
3.
right. Ignore me.
So we just do that, and then that lets you throw out. Eventually, it says, okay, look, this point that's always in these circles. Well, really, you don't can worry about the points at all. So you end up with this, and you're like, okay, so most of my things are 8. So my radius is probably 8, and likewise for X and Y. And so you, in the end, say, okay, it looks like the circles I care about are all of these. Then what I do is I average all of them to get every last bit of quality out. And then I get this. And then I say, all right, now as a last step, once I have this guess, throw out all of these bad points and then redo the averaging again, because it sometimes is the case that some points, like you get this kind of thing where, this one is egregiously out, but this one's like a little bit out. And so you can't reject it, but once you get an average, you know that it's a bit too far from the others. So you're a sneaky one, you get tossed out too. And then we go back and we re-average, and then we like really. So these are all the little squeeze. You squeeze that all out, and then you get that, right? So that's working pretty good. And when you do all that, typically you get about 1/10 of a pixel accuracy. So great success.
Congrats.
Best case, you get 1/20th of a pixel accuracy. And like I said, best case, it's actually unlimited accuracy, but we have 8-bit data and a ton of stuff. So I'm happy. This is fantastic. Great. I figured it out. I totally got it solved. And that's the end of section 5 before everything goes to hell again. So
what a cliffhanger. Was it in section 4 though?
I don't know what section. I guess this is. Yeah, we're about to hit section 6, which is where I'm humbled.
Okay, can we do a summary of section 4/5? Like to go through all the steps one more time to make sure that we got this one in sequence.
You mean in terms of like what we've discussed so far?
The algorithm, yeah.
Oh, right. Oh, yeah. So the algorithm is basically. We're still not at the final algorithm, but we're getting closer. But the current one is you threshold the image based on color, hand wave. You figure out, you reject a bunch of blobs. I didn't talk about how we reject the blobs, but Rick's algorithm knows how to reject some of the blobs. So reject some of those blobs, hope you found the right blob. use area averaging and then square root to get the initial estimate. From the initial estimate, cast a bunch of rays along the pixel values, look at the values along each ray, and each ray independently fit a sigmoid to each of those rays. Once you have those points, do brute force consensus sampling to reject any rays that wildly disagree. Once you throw those out, circle your wagons and then reject any other samples that kind of are on the edge. Once you have that, then you have something that's roughly to a tenth of a pixel. It relies on knowing the point spread function width, meaning like how much that sigmoid varies. Because if you didn't know that it's a constant amount and you didn't know that amount, when you're fitting the sigmoid, if you let it wiggle, now that's changing your edge width. And now that is part of your solver and you can't tell the edge reliably. So this is why when people have asked me like, can the move algorithm be replicated on PC? I'm like, I don't know, man. Because
with
it's an arbitrary camera. And you'll see I end up squeezing even more out of this camera because there's more and more things I can find in there to sort of leverage. So it's incredibly tailored to this camera. Now, you can repeat the process for your camera, but I don't know how you would repeat the process for an arbitrary camera without like an extensive calibration step. So, that's kind of the thing. And so this algorithm's in the patent, by the way, so we can look at the patent later. I think it's probably going to expire soon. This was like a long time ago. But we actually tried to take it to computer vision conferences. Like Rick tried to take his algorithm to computer vision, the non-bounding box area one. No one wanted to publish it. So even though he has like a PhD and has a standing, everyone's like, this is weirdly hacky. Like, what if it's not a sphere? What if it's a box?
It doesn't look like a nice academic paper, Like it's
like reject the blobs, take the square root. It's kind of a circle.
Realistic, complications. Like it's not theoretical enough.
Right.
So I think about the only remaining question I have is like the final thing you were showing in the simulator clearly had some distortion on the sphere out toward the
foreshadowing
corner
for section 6.
Okay, well if that's where it comes in, because I was like thinking about the sort of ransack and rejection and consensus process that you're doing. I'm sort of like the first phase seems like it would work fine. The coarser occlusion thing where you're like, this radius is wildly different, throw out that point. But then if you try to do a finer thing, surely you're just going to reject all the ones on the long axis of the ellipse because it's distorted now. And you're going to like just throw all that data away? I don't know.
You were the right man for this podcast.
I still don't even know why Wookash invited me, honestly.
He had a sense.
I'm very happy to be
he's
here.
The host. He knows. He's like,
I guess.
I know the right person to invite.
What am I supposed to say?
So exactly. So going back to what we're looking at here.
Are you about to start the section 6?
Yes.
Can we also do a couple of questions? I asked in the chat other questions. So before we start, open a new section. Is there a meaningful color fringing at this resolution when using a simple RGB LED in the controller? Color fringing, I'm assuming.
Well, section 6 is about to get you. Yes, okay. There is. Any other questions?
If I was about to also ask if you need to fit an ellipse at the edges of the frame.
Okay, so that's basically my question there. Yeah. Okay. I'm enjoying this a lot. Probably a good 15 to 20% of why I'm enjoying this is it's starting to explain why the photos that I take with my DSLR look really crap too. So I think I might be learning a couple general things in the process of this, even beyond computer vision.
Yeah, I had a blast writing this simulator. I have, because I did all this stuff, and over the years, I also wrote a camera simulator for Google for internal purposes for machine learning training. Because it turns out when you're doing machine learning and trying to teach these neural networks how to work on these crap images, most of the simulated images at the time when I was working there and just across the industry, people would just render stuff out of like Blender or whatever. And those pixels, as you saw, are way nicer than what you actually get on a real camera. And for a while, people just ignored it. They're like, well, look, we can train on, and they're like, synthetic data is not useful because it doesn't have the characteristics of a real image. And therefore, like, people found out that if you train on synthetic data, it doesn't really transfer to real world images. But when I joined Google, I was like, bro, but you can simulate that. Like, and so because I knew what a crap image looked like and I knew what the pieces of the crap image are, I was like, I will write you a full pipeline of how to make this image awful. And so we're about to see some of that in section 6. And so I kind of went through all these understandings of like how the noise is modeled, how the different distortions are modeled, how the aperture is modeled, and all that stuff. So when I talked to Wookash, I'm like, I want to explain this move thing. I think it's going to be kind of interesting. He's like, I don't know. And I'm like, I kept trying to show him like the image is really bad. And he's like, how bad is it? And I couldn't explain it. So I was like, I'm just going to write the simulator again. So because I already have done it before, it was relatively quick for me to like piece it together. And IMGUI is great and shaders are easy now. So I'm just like, you know, ray tracing in the compute shader and the computer's fine, doesn't care. So yeah.
And also Anton is the demo guy. Like, it's always about the demo, you know. So
That's right.
If you can quickly get together and have a simulator, it's like, hey, look at this demo. It's like, oh, that's so cool. Let's do it.
That's right. Yes, got the job. All right, let's jump into the next bit. All right, so as Ben noticed, when we're in the corner of this image, we're zoom out a little bit so you can see better. We'll get rid of the plot for a second and we'll drop our exposure so you can see it. So pan out, unzoom, 0 everybody. Okay. So you may notice from this image that as I move to the right, the ball stretches out a little bit. Maybe hard to see, but when I move to the top, you can now see it's a little bit elliptical. And if you zoom in on it, you can really see it, especially if you, as you move, you can really see it become spherical again. And then, you know, we'll go to this corner of the image, see how it stretches out.
It's becoming cartoony.
It's becoming cartoony. And it sort of is nothing to do with it. The camera's actually quite good with this respect. Most cameras have what's called barrel distortion. So they not only have this, which is perspective distortion. This is what happens if you rendered a sphere, you know, in your game, you're going to get this. This is just perspective distortion. Most cameras also have what's called barrel warping, which also like pin cushions your corners. PlayStation Eye, being designed by a computer vision researcher, does not have barrel distortion because that's why it has that long barrel, because it's an extremely long throw. So there's a couple of interesting things about the PSI that make it, like, the reason you see PSI, at least in that era, being used in computer vision research often, people were like clampering for like PSI drivers for PCs because it's actually a really good computer vision camera. Like, and it was cheap, you know, compared to like a real computer vision camera. Anyway, luckily it doesn't have barrel, but it does have perspective. So I was very happy my edge fitting algorithm worked, but when I go to the edges, my ransack would throw everything out. So I had two options. One is I don't run ransack, but then occlusions from handle don't get thrown out, and that modifies it. And also just the answer is wrong in the corner because it's sort of like averaging a bunch of rays that are stretching out, or somehow figure this out. Turns out that the projection of a sphere under perspective is always an ellipse, which is sort of counterintuitive. At least it was to me. I always imagined it would be an egg, but the perspective projection of a circle under perspective is an egg, if a planar circle, but a sphere always projects to a 2D ellipse. So we know it's an ellipse. And we also know, again, I'm just freewheeling.
Excuse me, but
Probably,
what shape is egg if not
egg?
ellipse? I don't.
You know, like an egg, like
It's kind of like fatter on
like
one
a real
end.
egg. You know, egg is fatter on one side.
Is it?
Do you have elliptical eggs in Europe?
Okay.
There are elliptical eggs.
Like,
some birds have elliptical eggs.
Okay, like this mid thing is not in the middle. Like,
Yeah.
Okay.
Yeah, I mean, eggs aren't perfectly symmetrical,
Okay,
right?
okay.
Some birds apparently do have symmetrical eggs. So, but I was like, Wookash must be eating some really fancy eggs if they're symmetrical, rare endangered birds.
Okay.
They just throw out all the eggs that aren't elliptical before they sell them to them.
Send all the the egg-shaped eggs to America.
Yeah, they're ransacking the eggs.
Okay, somebody actually posted emoji of an egg, and I see it clearly. Okay, it's fine. It's fine. We can move on.
You see it now. Now you can't unsee it. So, but it turns out we don't have to deal with that shape. We actually just have to deal with a normal ellipse. And again, if you're a computer vision person, there's a way to like actually you can undistort the stuff. I was just like, okay, well, it looks to be getting worse towards the edge. And so we know the estimate of where it is from the center. So based on the distance from the center, we can know how elliptical it ought to be. And we also know the axis on which it's going to be elliptical, right? Because as we move around the image towards the bottom left, it's elliptical this way. Towards the top left, it's elliptical this way. On the sides, it's just elliptical horizontally. So we really just have an axis and a distance and the amount of ellipseness. And so I worked that out. I'm not even sure I did it mathematically. I might have just, again, I have one camera. So I'm like, okay, it's this big in the corner. And so what I do is that I use that initial estimate to squish the rays along the axis from the center, because I have that initial estimate. So I shoot the rays through the raw image, because the other option would have been to shoot the rays in an elliptical fashion, but I don't want to do any resampling of the image. We're already like barely debayering this thing, so I want to walk the true pixels, like not anything processed. So I walk the true pixels. Now the edge is a little bit warped, but it turns out to be okay. And then once I get the results, they're all elliptical. And before I ransack, I take the centroid and I squish it. So effectively, what it looks like is the same thing as a sphere or a circle, but in the corner of the image. And so that.
And does that basically just mean that you're sort of interpreting the, like, I don't know, you're sort of like squeezing the points together on that Luma graph that you were showing?
Yeah, so I squeezed them together around the center of what the estimate is. Now, if you get really precise, turns out that's incorrect, because that's not actually where the true center of the sphere is. The true projected center of the sphere, I think, is a little bit closer to this side, because of, the projection is an ellipse, but the center of the ellipse is not the center of a sphere. So you can actually work out where the actual center is. I don't believe I actually account for that. It just didn't seem to matter. Plus, when you're at the outskirts, it's, well, like someone said, you actually have this thing called aberration. So it actually looks more like this. So you get color fringing towards the edges. That's one. So your chromatic aberration starts to split your image. But not only that, you get what's called coma aberration from the word comet. And this I found out from astronomy telescopes. Turns out at the edges of images, you get, it's a lens aberration. So it's not a fringing, but it makes this kind of comet tail. So the blue is not the same size as the red. So the fringing is discontinuous in different directions. And you can sort of imagine when you're at this point, the hue tracker is not even getting anything. It's like the hue has been shifted. So then you have to increase the threshold. You get something like that for your initial guess. So you start there, and then your rays try to deconstruct it. You pull apart the ellipse. It's not pretty, but something comes out. I never got a correct adjustment for the point spread for coma aberration. It was always on the list of things, but it just, in the end of the day, never made it. So I do the elliptical correction. I have thresholds that are sort of wide enough that coma has to not fail. So we find the ball, but the accuracy at the corners is not as good as it. So if you're watching and you want to do this the right way, got to account for coma somehow. I didn't. By the way, this is what the full image looks like with and without the aberration. You just kind of see the corners, and it's probably pretty subtle on the stream. But you could see how bad it is. Like if you don't have the aberration, the ball is more or less getting picked up. But when you do have the aberration, now you're really starting to, and if you have actual noise, not paused, it's looking like that, right? So all that, the noise is going bananas. So again, your estimate for the size of this thing purely based on pixel count's not very good. In addition to that stuff, you also have vignetting. Vignetting is the darkening of the corners of the image. So I should probably demo that when we're out here. So vignetting is this stuff. It's usually used as a film cute effect, but it's not cute on a camera. But you have vignetting towards the corners, which eats into your image, probably about this much for the PlayStation Eye.
But this is something you can turn off through software, no? Like inbuilt in camera?
It's different for every camera because the sensor position varies between cameras and therefore it changes the amount of vignetting. And we don't factory calibrate PlayStation Eye cameras because it's so expensive. You can't do it for a consumer grade camera. Literally every minute you add to the factory line costs money in the production. And so if you have to take the camera off the factory line and show it like a checkerboard pattern and calibrate it, it's like you've now gone from a camera that's, I don't remember, $35 to a camera that's $800. So it's just not tractable. And then now they do. I mean, they figured it out, and they, like, I think Oculus and other, I guess Facebook, whatever, Meta, I don't even remember. Basically, all the VR companies calibrate their cameras because you have to, but that's part of why the headsets are more expensive. And the PlayStation 4 camera, I believe, was somewhat calibrated to, like, I think, yeah, it's checkerboard calibrated. But again, the problem is you don't want to touch the pixels. The pixels are like, you only have 8 of them or whatever. So you're like, don't touch my pixels. Don't make a mistake. So the real problem with vignetting, and this wasn't much of a problem in the PS3 camera, but spoiler alert for PS4, it turned out to be a problem. The vignetting can be colored. So you can get this case where the corners of the image are not just darker, they're slightly different color. It's not a lot. It's a minor tint. It's not like quite this severe or whatever, where you have red and this kind of thing. But it's enough that, look, if you bring the vignetting in, look how it's shifting the ball. And I can zoom in and show you. As the vignetting comes in, it changes the hue of the ball and it messes up your color tracking completely. So it turns out that you have to basically have your tracking wide enough, margins wide enough to account for vignetting across all the cameras that you might run into. And that's kind of that on that front. So that's a thing. Edges can be better, not completely, but not bad. The other issue is color noise. I won't go into that too much right now, maybe later if we have time. But the other thing, now we get to motion blur, which is what Ben mentioned before. It's like all of this is working now, brilliant. Edges are not too bad. We're getting, decent results at the edges, 1/10 of a pixel most of the time. But when you're I'm mostly doing things still because, again, we're just trying to get this thing to track, man. Come on. So now we're at a place where this thing's actually usable. So like it's tracking pretty well enough. We also by this point hired Eric Larson, who is another great engineer I worked with, and he worked on the sensor fusion. So I'm not even talking about the sensor fusion, but by this point we have integrated inertial measurement units and gyros, accelerometers and gyros. We're fusing the signal. We've got the Z from the X, Y, and Z coming from the vision. We're fusing it. And now we're noticing when you move quickly, predictably, it's not working so great. And at that point, we're like, okay, this is when I have to start looking at the image a little bit more closely. And so I'm like doing a bunch of these tests where I have one button, one key, one hand on the button, and I go, huh, and I go really quickly and I try to freeze frame like a motion blurred image so I can look at it, or like record a video or whatever, and then freeze frame that thing. And what that starts to look like is like this. So if you have some velocity, so here's velocity, like your beautiful ball is no longer a beautiful ball. And this kind of blur is rare to see. This is pretty extreme. But blur is proportional to the exposure of your camera. So basically, if you have high exposure, you're going to have more blur because the shutter is open for a longer period of time, so you get more blurring. If you have low exposure, I don't have this in the simulator. This is all separable. But with low exposure, you have less motion blur. So you have to find the middle ground. Like for tracking quickly, you want low exposure because you want to basically blow out everything in the background that isn't the sphere. The sphere is glowing. So the sphere's ideal condition is everything's black. So basically what we're trying to do with the camera is like run the exposure as low as possible and brighten the LED as much as possible. So oftentimes we're running, something that looks fairly like this. And then that's better than, the opposite because it lets the color tracking be more accurate. But if you pipe this image into your augmented reality game, obviously it's too dark. So then you crank up the gain and it looks like this. So now this is obvious from anyone who's used a DSLR. If you have a high ISO, you get a ton of noise. You get fast shutter speed, so you capture less motion blur, but you get a ton of noise. So that's why PlayStation Move, for one, a lot of the AR images just don't look very good at all compared to how good the camera could be because it just can't track with high exposure. But also it has two operating modes, AR mode and VR mode. AR mode assumes you're not going to care too much about tracking. You're probably playing a party game. It's probably the cool part is that it's a camera feed. So we allow for more motion blur, tracking quality degrades. If you're playing what we called a VR game before VR was like an actual thing, we just needed another name, which is not showing the video feed. So a game where you're like playing with swords or whatever, we actually kill the exposure. We don't show you the image, so it's fine. We can just nuke the image, and then the tracking quality can be better. So you had a choice as a developer. Are you going to make a camera game or a non-camera game? And there were kind of two classes, and sort of party games were worse. I did do some things for it, though. So just like, so in the corners, we know how much to squeeze the ball by based on just pure geometry of the optics of the camera. For motion blur, you would think, okay, well, so it's stretched out. Whoa, wrong slider. By this point, because we integrated Eric's code, we knew the velocity from the inertial measurement. So even though we don't know it from the image, we have the advantage that other pure vision people don't, which is we get a velocity even though we don't know where the ball is. So I take the velocity estimation and I do the same trick that I do with the corners of the image. And I, again, squish the rays together based on a scale factor of how far away it is and all this camera intrinsic stuff. So that's how we deal with motion blur. And then we get the best bug that I came into. So question before
you do that, can I just, does the sigmoid fitting thing, like, is the... You said that the point spread function is this nice sigmoid shape. Is that true of motion blur as well?
I think the motion blur is a linear ramp, if I recall correctly.
Yeah, that's intuitively what I would
think that's
expect,
correct.
I
think where there's overlap, it's a little bit more complicated, let's say. Yeah. But I think it's effectively a linear ramp. And so what ends up happening is you're fitting a sigmoid to something that's like a sigmoid blurred ramp, which is like a wide sigmoid. And so in practice, what happens is the center, how do I say it? The center of that ramp is still what you want to find. And you're fitting a sigmoid, which has a center. So what's happening is your fit is just less correct, but it's still going to find the right place, just more noisily. And so in practice, what it means is like that whole thing I was espousing of like infinite resolution. You can do it. You can't because of all these things. But in practice, it still gets the correct scale of the answer, minus the noise.
It's just more noisy, which still is bad.
Because you do know how much to squish it by. It's just the shape of it isn't quite right, so the fit isn't quite as good.
So I think, if I recall now, I'd have to remember it. I may even squish the samples before, like I find the samples and then I squish them, or maybe I squish the results of the edge fitting. I don't remember. But yeah, basically ad hoc squishing is what we do there. And when we're integrating this data with the accelerometer and gyros, like this is a good point to pause. It's probably obvious for unless people on the call have done tracking. Accelerometers are always measuring gravity. So they're always measuring the acceleration due to gravity. So it turns out that even when you're not doing anything, gravity is sort of a signal, a vector signal inside your accelerometer. And so you can use that to know the tilt of the controller. Because if it's tilted this way, your gravity vector is like this. You're tilted this way, you see like a vector relative to your body. So in the reference frame of the object, your signal is rotating, and that rotation tells you the tilt. But if you move the controller like this, nothing tells you anything because gravity is down. And so the rotation around the gravity vector, which is called yaw typically, has no signal of rotation at all. And we don't get any yaw from the controller either. So yaw is this thing where we don't have any signal. And this has been known from the beginning, but we just sort of swept it under the rug.
In an accelerometer specifically, or with an IMU? Because I thought a gyro would tell you the yaw. I guess how many axes do you have on your gyro?
So the gyro is a 3-axis gyro, so you get it, but the gyro tells you the velocity of rotation. It doesn't tell you the absolute heading. And so if you zero it and then you start integrating, it tells you the heading as you integrate. But remember, we talked about integration. Every integration integrates noise, and these are 2007 gyros. Even with non-2007, that noise builds up into what's called yaw drift. And so what that means is over time, the controller, if the user is not manually saying this is zero, it will drift. And so if you remember when the Wii U Advanced or whatever the attachment came in, that was a gyro attachment, and it would constantly ask you to recalibrate it. That's why, because if you integrate the gyro, you can only integrate it reliably for about 10 seconds or 20 seconds or something.
Mm-hmm. Well, yeah, I remember playing Skyward Sword and having to constantly be like either pushing it against the like edge of the whatever, or pointed at the screen so that they could use that as a signal something. I don't know. I'm sorry to keep hammering on this, but why do you care about anything other than the velocity if we're talking about motion blur, right?
The reason I'm talking about the rotation is because it kind of leads into the next situation. Okay. But yeah, for velocity, you need to know the rotation to know how to interpret the acceleration correctly, because the acceleration is in the body of the controller. And so if your rotation is inaccurate, you can imagine your acceleration vector is just going to be pointing in some odd direction. So you still need the rotation to be good. But this problem of rotation was kind of haunting us from day one, because we don't get rotation from vision. The ball's too small. We can't put dots on the ball. And that's why we hired Eric. So there's a whole parallel arc I'm not going to go into the weeds of, but getting yaw direction is like an equivalent problem difficulty to this like edge fit. So I'm basically edge fit guy trying to get the Z coordinate, and Eric is like basically yaw guy because we can't freaking get the yaw. But early on in the piece, Rick has this idea. He's like, okay, well, look, we don't get rotation from the vision, but we can look at the path the user is moving down. And so like imagine the user is kind of moving towards the camera, right? So we know that the acceleration from the computer vision and the velocity from the computer vision is like towards the camera. And, maybe it's a bit noisy, but it's relatively okay direction-wise, right? And so we also know the accelerometer. The accelerometer, now, if we don't know the rotation of the accelerometer, we don't know which way it's giving us the signal. But let's say the accelerometer is sort of saying it's going to that direction. Well, if the vision is going this way and the accelerometer is going this way, we have a difference here that we can just compensate, because we know the vision's correct. The accelerometer, if it matches the vision signal, that difference is exactly the yaw. So we can correct out the yaw by comparing the vision and the acceleration data. Theoretically sounds good, right? Just like theoretically sounds like, yeah, there ought to be more data in these pixels. completely correct. So he actually wrote this algorithm and just like looked at the time series and compared the two things and tried to slide the time series, and it worked. And so like, again, theoretically, we're like, I think we can do this, right? But then we end up like hiring Eric because we're like, I think we can do this, but can you do better? And he's like, okay. And eventually he like goes on a quest and he does way better. But it's like, again, another one of those cases of like, I think we can, so let's just hope. The other approach is to use a magnetometer. Magnetometers are canonically used for this because a magnetometer measures the Earth's magnetic field. And that's like, it's like a compass. It's like basically a 3D compass. And so if you look at like, I don't even know these days, but I think on drones, you probably still get them. If you measure the magnetic field, that gives you a heading. And so that gives you yaw correction. But as we discussed with magnetics, they're completely unreliable indoors. And so up in the sky, where a plane is flying or a drone, magnetic field's relatively stable, unless you live in the North Pole, which points the hairy ball problem and compasses don't work very well. But in the US, Japan, and UK, where PlayStation operates kind of thing, magnetometers are reasonably okay. We used the magnetometers for a while in the US, and actually we had hardware in there to do that. But when we got to testing in Japan sky rises have tons of rebar, which is soft metal, and it completely destroys the magnetic field in Japanese homes. So when we tested in Japan, the yaw would just go bananas. And so we had the hardware, we eventually had to remove it like in post, like in the last minute thing. But we're like, all right, Eric, it's just you, man. It's just you and this noisy ass vision signal from my terrible Z data. And so it was kind of like me trying to do my best to get Eric, and like the XY accuracy is fine. He doesn't need it. But of course, if you compare the XY signal of the image, that gets you tilt. We don't need tilt. We already have tilt. What we need is the Z signal, the one that's the worst, right? So it's really Z and X. So Z and X is the values that Eric cares about. And so he's trying to fuse my values and run a Kalman filter and all this stuff. So then we get to a curious problem. Everything is more or less working. Motion blur is causing some issues. That's why I investigate motion blur. And then Eric comes to me and he's like, look, man, I'm kind of going out of my mind. This is weird. When I move the controller like this, and so now when we move the controller, the yaw gets corrected because it's using the Z correction. But he's like, it works really well, but when I do this, if I do this for about a minute and I stop, the yaw is like to the left. And I'm like, well, yeah, it's probably because there's a bit of motion blur. And so I investigate motion blur, right? That's what prompts me to investigate motion blur. Because I'm like, maybe it's not just the quality, but we realize that, when the motion blur is happening, maybe at some points you're slower and then those points appear closer. And when you're blurred, maybe you appear farther. And so if you look at that kind of from the side, if I'm moving like this in a perfect circle, if the vision kind of on the upstroke is farther, on the downstroke it's lower, then it will look like the data is skewed in a way, right? In this axis. And so we're like, okay, well, so probably something about this pattern is causing like a skew. And he's like, okay, but check this out. He moves the other direction and it rotates the other way. And so he's like, what is this, man? This is bananas. And I'm like, so we're like, okay, we're both like math people, Eric more so than me. So he's like, maybe it's like quaternion integration, like Euler angle, kind of like some kind of thing there. So he like deep dives into quaternion integrals and stuff. He's like, no, it's still there, man. And it's like, you don't have to move very quickly. And it's just, and so we try to like low exposure, still there, high exposure, still there. So we know it's not exposure dependent. It's not time dependent. It's not quaternions. It's none of that stuff. And I'm like, and we can't see it. We make videos. I look at the images. I can't see anything. So at this point, I'm like, okay, the only variable we have left is rolling shutter. That's like a thing I heard about, but how do we test if that's the thing? We can't test it. We can't turn the rolling shutter off. We don't have a global shutter camera. So I was like, okay, what I'm going to do is I'm going to write a simulator for the camera, and then I'm going to have a toggle to turn the rolling shutter on or off. And then we're going to send that simulated data into actual simulated accelerometer and gyro signal and run the whole library through as a simulation and see if that resolves the issue. Lo and behold, when you turn rolling shutter off, the issue goes away. And we're like, holy bananas, because you can't even tell the difference in the image. So here, I'll show you now what rolling shutter means. So like for people that don't, Ben knows what's going on here, but
Of course.
I only know this
Ben, of
because
course, knows.
one of my
Of
students,
course.
like a year ago, one of my students was making a big deal about getting a global shutter camera for the bot. And I'm like, who cares? We have never cared about this.
We would have,
but I'm aware of the concept
global
at
camera
least.
shutter. My God, I would have paid a lot for a global shutter camera. So you imagine that when you snapshot a picture, it just sort of takes the whole picture, because that's sort of how a film camera would work. But because of cost and other reasons that I'm not going to sort of get too deep into, the way most CMOS cameras work, and I think even now until today, is they read one row at a time. So you're going to read row 1, read the pixels, and then a split second later, you're going to read row 2 and row 3 and all the way down to the end. And so this first row starts at t equals 0, and let's say that the whole frame time is going to be, a 60th of a second. This next one starts at t equals, 16.666 milliseconds divided by the rows or whatever. And so progressively, each row starts a little bit later than the last, and the last row finishes exactly at 1/60th of a second. So it's kind of like VSync in games, if you've seen like VSync tearing. But VSync tearing is just one line in the middle because it's like flipping from back buffer to front buffer. This is like per line is imaged at a different time. And partly this is for memory because it's cheaper to read out one line at a time. You just send the buffer over for one line. I think there's also like a reason for the circuitry. You need less readout circuitry, which makes it cheaper and makes better light sensitivity. I don't remember, but most cameras are rolling shutter. And that's why you also, when you take phone video, it's jiggly. It does this jiggle thing. It's because of rolling shutter. Okay.
The example that every time somebody takes a video out like a train, everything is like really, really slanted in the image. And it's like, oh, weird, why is that? But it's the same effect as I understand it.
I think that's correct. So it must be that it's still there. I think there's some deep reasons for why it's like a thing. And so here's what it looks like. Here's rolling shutter simulation. So
you have it turned on.
No? Sorry?
You have it turned on.
Oh, yeah?
Have it.
Oh, yeah. It's turned on. Well, if the ball's not moving, nothing's happening.
Yeah.
So rolling shutter on or off doesn't really matter. It's only when the ball starts to move, let's say in the XY direction. Now let's turn off motion blur because it's confusing matters. It makes this is why we couldn't see it, is because it's hidden by the motion blur. But when you turn rolling shutter on or off, there's a difference. Can you see it? Probably not. Let's have a look. Barely. That's how much difference there is. But because you're running at like 1/10 of a pixel difference.
Can you turn on the graph again?
I know, yeah. We should get the graph going, yeah. And let's kill the noise. So here's the difference.
Oh,
See
wow. Okay, now, okay. What the?
So this much error, because it's compounded over a long time, the Kalman filter, which is like the technique that Eric was using, it estimates the noise and the bias of the signal over time, and it would pick up a consistent bias in a given direction. I'll increase the velocity so you could really see the effect. Let's say it's like 5. Even at 5 meters per second or 10 meters per second, so you could see now it's squished and it's like sheared. But that part actually didn't matter. So if it's going to the right, you can see, or like in this case, it's going the other direction. You can see that basically lower lines are imaged later. And if you go in the other direction, it's going to shear the other way. Interestingly, that didn't matter because it sort of evens out as the ball is moving left and right. It evens out, so it sort of goes one way the other way. But the one that doesn't even out is the vertical
at the top
one.
and bottom of your circle.
That's right. So
it's the top and bottom of your circle that we're canceling each other out.
Yeah, at the top and bottom of the arc, the circles cancel out. But if you go down the image, now your ball stretches because it's getting imaged in the direction of the rows. Really accentuated. Here's 20, like 20 meters per second speed. If you're going negative 20 meters per second, your ball gets shrunk because as you're moving up, the image is racing you to the point. And so what was happening is that on the upstroke, the ball is slightly enlarged, and therefore it appears to be slightly closer, and therefore I give a slightly closer Z value. And on the downstroke, it's getting shrunk, or sorry, the other way. On the upstroke, it's getting shrunk, and on the downstroke, it's getting enlarged. So the top and the bottom are at the same Z coordinate, but the other ones are slightly skewed. And Eric's algorithm is picking that up as a bias. And that's a bias that's completely rotation driven. If I'm rotating clockwise, then, one side is. So after we got,
So basically it almost like rotates the plane that it understands the thing to be operating in. And it's like, I guess I wasn't understanding why that would like build up over time. That's the Kalman filter thing that's basically building up, and it's saying like, okay, this is what our Z motion looks like. Like this is sort of the plane that it's actually operating
like
in. It just sort of like slowly learns.
Well, at every step, it's basically seeing along certain parts of the path, oh, we're going back. And the accelerometer is saying, you're not going quite back. So like, all right, we'll correct a little bit. And then as you do more and more of the circles, it keeps saying like, we're always a little bit off from what the accelerometer sees. Because it's a repetitive motion, it just sort of like says consistently whenever, vision says we're here or like moving in this direction, accelerometers say we're moving in this direction. So consistently there's a difference between them, and it interprets that as the yaw error. And because it's consistently the opposite in the other side, it just compounds from both sides. Whereas if it was the other way, then they would kind of cancel out. But in this case, it doesn't cancel out, it compounds. So that's a case where basically we did it in the simulator. I still couldn't see it in the real image. We could barely see it in the simulator. When you crank it, you could see the difference. And then I do my same, hat of tricks. I'm like, I know the velocity. How do I squish my rays? I squish my rays based on the velocity. Yaw drift goes away. We're like, hallelujah. Like, it still can't see the effect, but it's there. It's in there. It's in the data. And so from there, we were just like, there was other things of that nature where it's like tiny biases ended up in yaw drifts. That was like Eric's plight of just like, the other crazy one is like the ball can be any color and it changes color based on your environment. Like we didn't talk about that, but we can in a minute if you guys want. But to track well, it looks at the environment and it sort of says, oh, there's no purple in this environment. That's why it picks purple almost always, because there's almost never pink in the environment. It's like the best color is pink. There's no pink in the room. I'm going to be pink. If there's any red, it's never going to pick red. And it very rarely picked yellow because usually there's yellow stuff. Like I have a yellow display there, and it's like things just look yellow. Yellow's common. But turns out sometimes it would pick yellow. And when it would pick yellow, the yaw would drift more. We're like, what? Well, yellow doesn't track very well. It's kind of like a bit poor. We basically sat and looked at it, and eventually one of the hardware guys in Japan, Enomoto-san, Hiro, found it. It turned out that the PWM frequency on the LED for the yellow color was cross-talking with the gyro lines. And so he had to move like the gyro lines for the gyroscope away from the PWM. And it happened.
So lighting up the LED a specific color just electrically interfered with the IMU?
Yeah, particularly for yellow. Like, because the way that LEDs are lit up is it's not like a voltage signal. It's called pulse width modulation. It's this high frequency kind of modulation signal. And this didn't happen early on, but then in one of the prototypes, the LED was doing these beating frequencies with the camera shutter because the camera shutter is pretty fast. So I asked Enomoto-san, like, Enomoto-san, crank the PWM, please, because I want the ball to be solid. He's like, how much do you want to crank it? I'm like, crank it to the maximum. So he did. And it was awesome. Like the move does not beat under any camera lighting. You have to have like 8,000 hertz hammer or something to get it to have any problems. But that high frequency signal, because of the way yellow looks or whatever, yellow just lit it up in a way that it made the gyro drift. So we had like all these like terror moments where we'd get a prototype and be like, this one yaw drifts, and it's like, scramble, figure it out. So this is the kind of testing I like. So I always kind of rail against unit testing to some extent. And I'm like, I like this kind of testing where I can open the app and diagnose what's going on. Like, I want to see all the data. I want like basically a visual debugger, and then I can run through my tests. And yeah, I have like some stored images of things I want to make sure as unit tests, but primarily I want to be like, when the hardware arrives, can I sit down with it for 3 days and just like really inspect where are the problems potentially? And if the problem arises, I need to drill down. And it might only happen that day because some dude walked in with a blue shirt and I got to capture that frame and analyze it, right? Like right now. So yeah. So that's the end of section 6. And
the bug section.
Yeah, this is like okay, we have it. We got it working. We demoed it to Kaz Hirai, who was like CEO at the time. And he's like, green light, we're demoing, we're announcing at E3. We're going to do it. And this is like, we think we can ship this now. And of course, no surprise, things show up that complicate that even more. But we can pause here and then potentially move on to those things or take a break. Up to you guys.
I have a quick question. How much RAM did Eric get for Fusion? Because you were like already at the 1.2 megabytes, and then you say like over time you need to have this like yaw drift. So like,
yeah,
how much time did?
Fusion doesn't need RAM. Like, I don't know, probably a couple of kilobytes or something. I don't know.
Okay, but yeah.
No, I don't know. Probably like 200K. I think it was like 200 or 300K for the library to do its thing, because he had to bring in like Sela Pack, and he used what's called an unscented Kalman filter, which estimated like covariances in a very nice way, because we have these non-uniform covariance matrices, and he can speak to that more. But it's not my area of expertise. But I think it was around 200Ks, and I think the library clocked in at like between 1.5 and 2 megs, somewhere there. And I was using 1.2 something because I had my 4 images to work with, and that was it. And then he was using like whatever rest. Yeah.
Nice. I think we can take a bit of a break. As far as I understand, we have like a hard out at 1 hour from now.
Yeah, we've got about an hour.
We could probably target like 30 minutes more. Is this fine?
Yep. Yeah, that's cool. From here on, it's mostly story time. There's one more technical thing we can discuss if we want to get technical, and there's more stories, and we can be light on technical from here on out.
Let's come back in like 5 to 7 minutes. Okay.
Sounds good. Yep.
Great. Short break intermission. Unit tests ignore reality. How are you doing, Ben?
I'm doing well. I'm having an amazing time with this whole thing. This is very fun. I'm glad you randomly invited me.
Why say you randomly? I purposefully invited you. I thought you would be a great fit. I didn't know you knew anything about like this particular subject, but you happen to be Mark Cerny in disguise, knowing all the back of the napkin. You don't even have a napkin, you just came up with the...
I'm not exactly coming up with numbers, am I? Yeah. Well, anyway, it is very fun. And yeah, I don't know. Mostly I've just been disappointed by simple vision processing hacks for a good long time. I mean, I've been dabbling since I was in high school, I guess, because like, the types of things. See, these days it's actually like easier because first of all, the cameras have gotten better. Second of all, they give us these tracking tags, these April tags they're called. They're those QR code looking markers that And they just scatter those all over the field now. And so it's really easy for robots to tell where they are, honestly. It's like, well, all you have to do is like point 1 or 2 cameras at those, and the like magic full pose solve just kind of works. But the stuff that I did in high school was like, they just put retroreflective tape around the goals, and your robot, like, you could just have like a camera and a really bright ring of green LEDs around it, and that would make the retroreflective tape light up really bright. And so then it's like, okay, just hue threshold, because it's like crank the exposure down, get as bright of green LEDs as you can. It was absolutely, by the time that they phased out the green, the retroreflective tape thing, it was like blinding to be down near the field with some of these robots that had like, an array of 10 very bright, very directionally focused green LEDs, because like they wanted to be able to slam the exposure down to the absolute minimum on the camera, so that literally the only thing you see is like green rectangles. And then, I don't know, from there you just like fit corners and get a terrible estimate of where the target is. And that was kind of all anyone ever did. And now, like I said, it's kind of just easier because they just scatter these tracking tags all over the field, and you can just run a Raspberry Pi or something that can do like a full 6 degrees of freedom pose solve once per tag for 2 cameras, and just like merge the poses together, and you've got something good enough. So I don't know. We don't do as much of the simple math that we see here now, and it kind of makes me sad.
I wonder to what extent, like, I wonder if pound for pound or like pixel for pixel, if modern techniques are actually more accurate, because I'm not sure they can be. I think a lot of the advancements was from higher resolution cameras and just more frames averaged and just higher quality lenses and stuff.
It's funny you say that. I mean, obviously, like when you're working when your experience comes from a high school level competition, it's not like you necessarily have a good picture of the state of the art. You're getting like downstream consumer versions of a lot of things, and you're getting wisdom of an immature crowd sometimes, I think. A lot of, to the extent that like sometimes people are using a tool that seems very mathematically fancy, but then obviously kind of fails in practice. Like when there's like a method in OpenCV called solve PNP. I don't even remember what PNP is for, but it's just like a full pose solve.
It's like if you input points,
the actual, because if you input the actual, these points are located exactly here, and then identify those points in the image, and then it just does a 6 degrees of freedom solve, and it's like brilliant. That's where the robot is. And nobody stops to think about the fact that as soon as you like, in that year there were these like plastic panels that you had to stick to the wall with Velcro, and they would like cover up the bottom of the target. And now your corner identification is just wildly wrong because most of the target, like, corners of the target are obscured. Well, it didn't really. Teams were like finding that their robot was in the ground pointing up at the target or above the target looking down. And it's like, what are you doing? The robot's on the ground. Like, this is a hard constraint of your life. I don't know why you're doing a fully unconstrained solve. The robot isn't rolled. The robot isn't elevated off the ground.
That was the vibe. I mean, again, like, I learned a lot from the computer vision community, but on the flip side, a lot of I think because there's an incentive for like pure math and generality, these kind of methods where it's like this method takes n points and connects them to n other points with like a known least squares error metric. And it's like, that sounds like a good publishable paper, but in practice you're like, okay, can I constrain this thing? Well, not really, because the solve is like just doing this mega linear algebra thing. Can I ignore the points? It's like, yes, we recommend you ransack the points, but that's like half the problem. Like, this is not even like.
Yeah, well, and the funny thing was, like, we had in an environment like this, like the height off the ground of all the targets, the height off the ground of your camera or the angle of your camera, and you can just like, basically you need maybe 2 points identified on the target to get a complete 6 degrees of freedom solve using simple trig. And
it's like
you know,
probably
you can get
frowned
better
upon,
with
right?
more
'Cause it's
points.
like, well,
but
what if we move the points? And you're like, well,
you can't move the points. The points are decided by the people who make the field, right? It's like this point is here at this height off the ground 100% of the time. So
yeah, I mean, on one side, I feel like the deep learning revolution solved so much of this, because now that you see all this stuff, you're like effect after effect after effect, and it's like, you know, not this is just for a single tracker. You know, when we tried to publish any of this, people are like, we were basically told tracking a glowing sphere is a completely solved problem, and we're like, I wish that was true, bro. Like, please show me the paper that completely solves the problem. They're like, you're literally doing everything to make your life easier, and it's still like hellish. And so I think the reason people were so excited about deep learning is because if you're a computer vision researcher working like 2012, you're like so thrilled to be like, this black box solves all of it at the same time without me having to hand tune all of these little things. Like, that's a huge win. And oftentimes you tune it wrong and you just go insane. And obviously, like, my thing just worked for the PlayStation Eye and the Move with a glowing LED, with all these things, right? Imagine now tracking an arbitrary object with no lighting under any, it's like, it's insane, right? None of the same kind of mentality of, this is like the optimization version of computer vision. It's like, I know this is my CPU, I'm going to optimize to like these CPUs. It's like, that's the computer vision equivalent. But if you want to write generic code, it's like, you gotta, go wider somehow.
We gotta finish the Move arc. We need to come back.
I'm delaying it now.
I've got an extra half hour, by the way.
Okay, that's good. Because we have a lot of things to cover, actually. I wrote it to you on Discord, like to list them. It's like section 7, we need to go through release of PS Move, reception, aftermath, and how tracking looks like today. That's a lot. And
we might have to come back to how tracking looks like, but
outro segment as well.
We can rapid fire all of it and then go deeper into any of these things. So I'll do like a quick. Let me go back to the timeline then. How about that?
Yeah.
Let's see.
When did Kinect? Yeah, I think I've seen the Kinect on your timeline. I think we should also because we mentioned Wii, but also Kinect came out.
Right. So let's see. So I join here. It looks like I started at around early 2008 because that's when we filed the patents. 2009 we unveil it at E3. So like the initial like meeting with the executives is somewhere here, and then the green light meeting is probably a month before E3, and then we launch. So the whole thing was about a year and a half, probably, from start to finish. The unveil is here, and then we spend about a year. It's more like this year and a half. The actual release is early 2010, and then the Kinect release is like a month after us. And then I go on the road to do PR, so I'm in a bunch of I'm on E3 stage and all that stuff. We get a surprise patent troll here, so I participate in a lawsuit against this technology, so we can discuss that and patents things if we want to go there. And then late 2012 is the first PSVR prototype. I can show maybe some sneaks of that, which is basically 3 Move controllers glued onto a head and displays done by another guy named Jeff Stafford. I think Oculus is around this time as well, somewhere here. PS4 is 2013. Dreams also unveils here. So along the road here during my PR days, I meet Media Molecule, and sort of we kick off Dreams in an obscure way. So there's like a Dreams arc in there. And then PSVR E3 secret demos start around 2013. PSVR unveil is like 2014. And then I think the first playable is like 2014. So probably releases here. I don't have the release here. Dreams of releases way out here. And PSVR 2 releases way out here. And to my knowledge, you can actually still use the Move on PlayStation 5. But like effectively, this is when the technology is superseded. So I think it's kind of cool because it survives 3 console generations. It works on PS3, it worked fully on PS4, and all that crazy over-engineering we didn't really get used on PS3, but when we came to do the PSVR, we effectively had like pretty capable 6-DoF tracking controllers, like straight out the gate. So like Oculus started out, they had like a display and just the inertial tracking because, and that got a lot of hype. But we were already doing a prototype where we had both hands and a head tracked, just basically strapping moves to everything. And so it was ugly, but then there's a PSVR story arc that's probably we don't have time to go through, but I wrote the tracking for PSVR as well, like converting it from that version onwards. So yeah, and we've obviously used it on Dreams a lot.
How did the release go, and then your move PR arc, and then the lawsuit?
So we basically we did the unveil, which was like the E3 unveil, and everybody was really excited, and we were at that point we basically had it working. The yaw was still drifting here and there, so we had to like reset more than we would like, but Eric Hero improved it, and the color and the rolling shutter improvements I think actually happened around this era too. There's also one more kind of like road bump, just like shout out to the team in Japan, because basically after like around this time, it wasn't the final design we unveiled, but like the team in Japan took over the physical design of the controller, obviously, because they're in charge of the console and the branding. And so after we thought we were basically done and we're about to ship this thing, they were like, can we not use a sphere? Can we use a different shape?
Product manager vibes.
And I was like, no. And they're like, we really want to. And so they made like prototypes. So basically it's like a capsule diffuser. And you can imagine why that's cooler for a controller, right? Like you don't want this glowing ball thing. And so
But that would mean then that different orientations of the controller, you would basically not see anything round at all.
It's just nothing would work at all. But explaining that to somebody who's non-technical, it's not their fault, but they're like, well, it's a glowing thing, whatever, right? And it's like, and this was before remote work, right? So the time difference between Japan is like large, and so Japan would go online at like 4 p.m. or something. We'd have meetings until like 7 discussing this stuff. And eventually we were like, their hardware quality was amazing. They were making great stuff, but like we just had no real relationship with them at that point. So I was like, not me, but like Rick was like, we got to go to Japan. So we all went to Japan and just like did a lot of izakaya time, just like drinking and eating yakitori and all that. And eventually like, I basically had to go into big demo mode and explain like what are we actually doing, because I think until you sit through like what we just sat through, people are like, yeah, what's the big deal? Like, and we're like, no, we have like 4 pixels. We're trying to we're barely making this thing work. And so until then, ironically, like this prototype was like the best diffuser we had. It's like a ping pong ball with an LED inside it. And then to diffuse it, I literally took a piece of a Safeway plastic bag back when we had plastic bags, and I taped it to the LED. Like that was the best diffuser out of all the different materials. Like a plastic bag seemed to diffuse it very well. So that was the prototype. And then from then on, it just got worse until like 2009 or something, because the hardware would be higher quality, but the diffusion would be worse, or the shape would be incorrect, or the color would be incorrect, like something engineering wise would be busted. And so when we went there and we demonstrated everything to them, it all finally made sense. And then all the things coming out were like amazing. So the team was like, Rick was leading the software side on our side and writing some of the algorithms, like prototyping and some API for production and stuff. I was doing the vision, Eric was doing the inertials. That's it. It's like a team of 3 people. Later on, we got people to do demos. Hardware side was equally lean. On their side, like Miyazaki-san was the manager, and then Araki-san did all the mechanicals, and Emoto-san did all the electricals, and that was it. And there was a driver person. I think Nakamura-san, I forgot his name, unfortunately. maybe Enomoto-san did the driving. Anyway, it was very lean. But once we got those guys on the same team, they did amazing work to like make the sphere even. The final version as well. Let me see if I can grab it. Like the actual sphere is squishy, which means you can drop it. So it passes the drop test, which my sphere would have never passed the drop test. And you can full force whack it into a table and it stays rigid. Now, it's really important for it to stay rigid, but it's made out of this like special grade silicone rubber. And on top of that, it's baby safe, so you can chew it. So like all these factors that come in, and it's like strong enough that a dog can't chew through it. It holds up in time. It's tested against like smoke chambers. People in Japan at that time smoked a lot. So like smoke would yellow the sphere. And as you can tell, we don't want the color of the sphere to change. So like all these things sort of like came around that final push between the unveil and the release. And then when we released it, it was, I think the reception was good. Like if you look at the critical reception, it got good reviews. But it was the same split as iToy in a sense. Like the hardcore gamers were like, what is this? I don't need to wave around a glowing sphere. This is silly. And the motion gamers, people liked it, but the problem is the audience on PS3 just didn't have that many of those people to begin with. So it took a while for that to kind of level out, right? Because everybody already got a Wii if they wanted to do that kind of thing. So there was like, the critical reception was good, and we sold a bunch of units. I think there was like the sell, I don't know what the sell through is, but the sold units was like 15 million. So it's like a lot, we got a lot of them moving. But again, it's like, it depends on what lens you take it. I think the fact that it got later used for PSVR is a pretty good win, because that's one of the reasons we were kind of first out the gate with a VR headset compared to everybody else. And it's also why it was the cheapest headset, because we were using literally like 10-year-old technology, but kind of keeping up with their tracking at the time, which was, the Oculus cameras were global shutter, for example, like for reasons you now understand. So we were like there with our old World War II technology, kind of like battling it out. So yeah, does that answer the reception?
I think so.
Yeah.
How was it to turn into like a advertising marketing person from being an engineer?
I mean, I liked it because I felt by then I was pretty proud of what we did, because we overcame a bunch of stuff. So it was pretty easy to be positive, because I'm like, I legitimately knew how good it was. I also knew how bad it was, and PR didn't love me talking about the problems. So like, the only kind of PR technique I would employ is like, don't mention problems if I don't have to. But if people asked, I would explain like, yeah, this is a problem. This is, I never was like shy about it. And, I think because of that, begrudgingly, they let me kind of do it and present it and stuff. It's like both me and Rick were good at doing that kind of thing. And people felt like it was genuine, right? I did have one episode where I off the record slammed Connect and got in big trouble for it. So there was like a post online where like, Move developer slams Connect, because they did this demo where they were like tracking a sword with just the camera, and it was like a sword fighting game. And at this point, you can see why I would be skeptical that you could track a 6 degree of freedom object with a depth camera, like, because I sort of tried it. So I just kind of plainly said, look, I have no idea how they would possibly be doing that. I don't know how the demo's done, but it doesn't look real to me. And so that was kind of like a bit fighting words, but and my manager, not Rick, but other manager at the time, told me like that studio gave him a call and they're like, keep your dog on a leash kind of vibe. And he was like, hey, maybe people look careful, but they're not wrong. It's like, I don't think that game shipped a sword, as all I'll say in the end. So I learned that nothing's off the record, basically, in that interview, because the guy was like, off the record, what do you think? And it's like the recorder kept running, and the next thing, a tabloid piece. Like, thanks, guy. But Sony was really cool throughout the whole time, and, got to hang out with PR and stay in nice hotels and do that thing. I got to meet Danny Trejo. Do you know Danny Trejo? Is he known in So he's the guy in Machete, or like he's like action star Quentin Tarantino movies. It's like this grizzled. Here, I'll show you a picture.
I am uncultured.
Oh yeah, this is.
Oh yes, of course. Okay, okay. It's difficult to know by surname, but
Yeah. So here's he was promoted for this game called The Fight, and so his like Daddy Trejo would move controllers, and he was like, yeah, he was like that.
That's awesome.
And I think that's me, pretty sure. But yeah, so that was cool. Like you get to meet all these like promotional celebrities and that kind of thing. So that was like a fun time. And he signed the controller. So I have a signed Danny Trejo.
Oh, nice.
Controller. That's the one.
Can you quickly tell about the lawsuit and patent troll?
Oh yeah. So for that, the context is like I mentioned briefly that we had to do color calibration. That's an interesting technical topic in itself, but basically the beginning, we couldn't avoid all color calibration. In Rick's old demos, you had to hold the sphere in the center of the image. There was like a ring, you had to hold it there, click it. But because we needed to zero the yaw, and also because we needed to later on color calibrate the LEDs coming out of the factories are not uniform, so you can't predict like, oh, this is magenta, like what the magenta looks like on the camera. They're not. So what we do is when you hold at the very beginning of the game, you only have to do this once, ideally. You point at the camera and you click. And we designed this calibration process to be like as streamlined as possible. So when you point at the camera, that gives us the yaw because the user is facing the camera. And we account for the fact that they're standing off to the side because you need to sort of do the perspective thing. So that zeroes your yaw. During that split second, the color sphere flashes. So if you've ever seen this, if you ever use it, it turns off first of all, then it goes red, green, blue, and then it turns off again and it comes back. And so that process, what it does is first it turns off. That frame is, let me see if I remember. No. First it goes red. I store that Bayer frame. I have 4 frames, remember? So you got like, you store the Bayer frame for, plenty of room, no worries. So you flash the LED red, wait like a frame for the LED, for the image to roll through, take a snapshot. That's your red frame. You save just the Bayer image. You don't de-Bayer it. You don't got the space. You put that into one of your slots. You flash the ball green, take another image, flash the ball red. Now you have 3 Bayer frames, each with red, green, and blue ball. From there, you do a sort of simple color detection and de-Bayer locally on the fly. So then you don't spend your images, and you figure out where the pixels are that are successively changing from red, green, and blue. That's a super reliable thing. Nothing in the world goes red, green, blue, red, green, blue. Like that just doesn't occur. So you just look at literally the difference, look for pixels that go from red to green, green to blue. And that's like, I mean, if we could run that as a tracker, it would be perfect. You just have to run a blinking ball and a way higher frame rate and everyone would just get epilepsy. So you can't do that too much, but you can do it once during calibration. You get that, and then that gets you a perfect tracking without knowing anything about the ball color. So the ball could be like blue, green, purple, more or less. The next frame you captured is the ball off. You don't know where the ball is, but you're hoping it's exactly where it used to be. Because those are the pixels that the ball color is, because they're just turned off. So you get the albedo of the ball, which is like and so I think I don't know if we, so here, I'll show you why that's important. Because if you put the thing into a smoke chamber, which is a testing chamber for what happens in a smoker's household, you get that. So because the silicone rubber absorbs the color. So if you're dealing with a sphere like that, it's shifting your color enough that you need to know its albedo difference versus the standard. So when you flash it, then you get that color, and like, all right, you got a yellow sphere. This is like a real video about how do you clean your PS Move sphere using hydrogen peroxide or something, I forget.
Why do you have to know that if you already got red, green, and blue as filtered through that exact color?
You don't need, that's a really good question. You don't need to know it right that second, but you need to know it because if you change exposure, you need to be able to estimate the amount the lighting contributes versus the LED contributes separately.
I see.
And so you have to separate the lighting component and the RGB component. You also have to ungamma the image. So we have to end up having to run the camera in linear space instead of gamma space. It makes the image even worse, but all that stuff. So basically, after that, you get a sense for what the color of the ball is, like the color of the albedo, and then the actual LED, the 3 frames of red, green, and blue also tell you, hey, what does the red, green, and blue LED actually look like? At that point, you know where it is. You debayer locally just the ball, you get your RGB color for each sphere. So like your red, green, and blue colors are not pure red, pure green, pure blue. It's some sort of combination. It's sort of like red is mostly red, but it has a little bit of blue, a little bit of green. So now you have what are called the primaries. And now you know, okay, when I crank the red channel on the Move controller, it's going to create this particular color, which is like mostly red, but a little bit of green. And then you can linearly combine those colors. Light combines linearly. You combine linearly the primaries of the controller and the baseline albedo color. And so you get all that knowledge from 1, 2, 3, 4, 5 frames, point, and then you also, from the unlit sphere, get an estimate of the lighting in the room and how bright it is, so you can set the exposure appropriately so your image looks reasonable. So that's our calibration process. So reason it's related to the patent, we patented that process. And dude shows up and he's like, after we released the Move controller, and he's like, I have a patent on color tracking. And the lawyers come to me and they're like, we got to talk to you about this. Like, is this legit? Because Sony got patent trolled all the time. Like most, I don't know if it's all, but literally at my time there, I never saw Sony like offensively use a patent. It was 100% defensive, meaning like we'd file patents to prevent patent trolls for like this showing up and being like, because that happened with the Rumble pack in PS3 era or something. Like a tiny company decided it was going to sue Sony and they lost a ton of money. Anyway, so this guy shows up. He's like, I have a patent on color tracking. And he did. It was like earlier. I think it was prior. But I read the patent and it was like, if you know the color of the ball, you can track the color of the ball. Like that was the extent of the patent as far as I remember. And I'm like, I'm not sure you ever made this. Like, I don't think you've ever tried. There was no mention of exposure. There was no mention of like variations of LEDs. There was no, like, it was high level and it didn't, it was not implementable, right? So it was clearly a troll patent. Someone had the idea, they patented it, and they went on with their day. So I was like, well, what does color mean? And the lawyer's like, what do you mean color means color? I'm like, well, color is an abstract concept. Like Mantis shrimps have 14 channels of color. We have 3 channels. Camera has different primaries. The concept of color is not clearly defined. So therefore the statement, if you know the color, you could track the color, is not really meaningful. And they were like, can you explain that on paper? I was like, sure. So I wrote it out and then they dropped the patent suit and they were like, these people know more about color than... So basically we warded it off. And that was that. So that was when the color tracking kind of came about. And then henceforth we filed a bunch of patents for so I don't know. I mean, obviously, you know, I'm not going to get into... I think
it's like more than 30 with your surname, which when we checked.
Yeah, it was, we were prolific. So, you know, that at least we filed on mostly things we made, as far as I remember. At least for most of the stuff that I did, we at least would have made it in the lab. Doesn't mean we released it, but I don't remember. I mean, probably a couple were filed just completely as ideas and whatever. Maybe they'll get overturned, but primarily it was like, hey, we're going to do this thing. So I know there's a lot of controversy about patents. I'm not saying it's a good idea, but in this particular case, this is like, in my view, it was a pretty clear case of somebody who, yeah, they had an idea, but they hadn't actually implemented it. I don't think I don't know. I guess morally dubious whether you can claim an idea without having done any work furthermore and then not attempting to productize it. So anyway, felt like that was overall patent good. I don't know if the rest of my patents did good. I don't know if they starved the rest of the industry from implementing colored sphere tracking, but I'm not sure anybody particularly wanted to. Because when you look at like Oculus and everybody else, by that era, if you can get a global shutter infrared camera, that's way better because you can just make the LEDs way brighter. Humans can't see the infrared until you really crank it. And nothing's in the image. And it's global shutter. So why would you even do this RGB stuff? Unless you want to do AR gaming. But then even then, you just had a second RGB camera, slap the RGB pixels on top, like call it a day. So unless you're in this weird sort of timeline where you've got an RGB camera and you want to use it and you want to do AR on the cheap.
So maybe we can finish on this. Like at this point, PS Move is like 20 years old technology, right? Yeah. Both the VR and tracking from VR moved on. But also like generally speaking, I think like the technology of tracking changed to the point where you can have, as we mentioned, like an iPhone and track the QR codes with pretty much no problem. There's lots of like AI models in neural networks, convolutional neural networks to understand the image. So what from the PS Move era sort of survived as a technology to this now? How the tracking looks like now in terms of both VR but also like outside VR tech?
I mean, I'm not in that field anymore, so I honestly haven't kept up. I think what has improved dramatically is detection of things. So our cheesy detector of like thresholding by hue, that's not how people do it anymore, unless you're maybe in university, right? So you can detect a dog, right, of any color and any shape hidden behind a plant. Like detection has improved dramatically. I'm not sure that accuracy or precision has improved dramatically because those are purely geometric problems, as we just saw. So when you're, that initial step of where is the ball, I think right now will be phenomenal. It would never lose the ball, I would imagine. But that second step of like where exactly is the ball without any bias and without any, noise corrections, I'm not actually sure I know some effort has gone into it, but I'm not sure that if you were to do it today, you could do it much better. I don't know. I'd love to know if somebody's out there and they're like, oh yeah, you can, like with the same number of pixels, can you do better with today's technology? I'm not sure. You can throw more memory at it. You can throw more processing at it. That's true. I don't know how it would help. One thing I tried for PSVR, at least conceptually, was this idea for like, I think it's called like back rendering. So you take my simulator that I wrote, and it's like pretty reliable, but it's expensive, but who cares? We have a lot of technology. And so, let's say you found the ball roughly, but if I know the camera really well, I can render the ball really well. And so what they do in astronomy is they render like a fake planet, and they put it through all these filters, and they're like, does it look like what we have? Well, then it must be the planet. So now it's not perfect, right? Because multiple different kind of things it's not one-to-one, meaning you can have maybe it's like that, maybe it's not, maybe it's like a mountain or maybe it's a goat, you can't tell. But you like imagine an algorithm which said, okay, I know the velocity that the ball is moving at, I know roughly where it is, let's just render a bunch of versions of a motion blurred ball and compare it with the pixels and see which one fits the best and just try all those versions. If you have a ton of processing power, I think that could work really, really well, because now you're not just fitting like these edge shapes, you're fitting literally all of your prediction to all of your data. So I think that's probably the most optimal way to track it. Like if it's literally the Kalman filter kind of approach of like render your prediction, compare it with the data, take the difference, use it to estimate your covariance, etc. So if you can do that on the image data with a really high quality, predictive renderer, I think you can probably squeeze a lot out of it. I don't know if people are doing that. I know people do it offline for astronomy applications. I don't know if anyone's doing it in real time, but yeah, if I had a ton of power, that's what I'd probably try first.
But to be clear, that's talking about finding the thing in the image, not finding where the detected thing is in real life.
Or
would it be both?
What I would do is I would...
Because you were saying if you throw more processing power at it, you're not sure that it would improve the geometric part of the computation.
Well, so I would improve the geometric part by brute force rendering predictions and comparing them to the image.
Oh,
and then if I know
a ball here moving this way,
is it a ball moving like
would
this?
look like this.
Oh.
Okay,
and then you actually get crazy stuff because now you can actually predict the velocity of the ball from the motion blur. Like,
right,
or you can predict based on the rolling shutter. The rolling shutter now gives you information rather than gives you problems. So you use like the ultimate system would be use some high-powered, neural network detector to find the ball anywhere and be like, that's probably the ball. And within that vicinity, using your prior state, just predict a ton of variations of what it might be. And you can probably guide that and use importance sampling and stuff. Test against all those variations. Again, it's expensive, but fine. And then use that to say, okay, well, I think it's moving with this particular velocity and whatever, and characteristics and everything, LED color, lighting estimation, etc. Throw all of that error signal back into the Kalman filter along with your inertials, churn that matrix and get predictions back. And I bet that whole thing is probably closer to how like our vision system might work. I don't know. I'm not an expert in that, but I could imagine that. I don't know if people are doing that. I know that if I wave the iPhone around, it doesn't track. So, like there's a limit even to, like I said, detection's usually pretty amazing now. But if you move things quickly, like the move can track at this kind of rate. Like we tracked, I think it was like, we measured, who did we either met like Jet Li or Jackie Chan or something, and we asked him to punch. Or something of that nature. I don't remember. But we got like a top martial arts person to punch, and we measured how fast they can punch. And I think it was like the rotation speed was like 2,000 degrees per second or something like, or maybe more, I don't remember, like some thousands degrees per second. And so we spec the gyro to that. Like, just make it Jackie Chan grade. And so you can wave that thing incredibly fast and still keep up because the exposure is very low. So usually most systems are not on that level.
Nice. I think that's the point where we're gonna end. Anton, thank you so much for prepping all the simulator and the talk and going through all this. This was really awesome. You want to say something?
Thanks for joining me for this crazy adventure. It's kind of fun to talk about it and like get a blast from the past. So I'm glad people are still curious about this sort of crazy over-optimized engineering to a specific case. Yeah,
that was amazing. I'm very glad that I got to be here to ask nagging questions and to dig into how all of that actually worked. I mean, it's all the kinds of things that I enjoy in engineering and programming kind of all jammed into one project. So, and I appreciate the simulator because it does like help, I'm so glad that we had more than just like whiteboard drawings to explain all these subtle things about imaging and all that. It was very interesting.
The simulator moment where you flip from an image to height map, this is going to be the first thing in the coming up, like the first thing people are going to see, because this is just like mind blowing. And then
I wrote that last night because I was like, you know what? I think we need that. We're going to need it.
It was last night edition. Nice.
Yeah, when I texted you, I have a cool demo. I was like,
nice.
10 p.m. I think I'm going to write this.
Nice. All right. Thank you, everybody. This will be available immediately for members in this unedited fashion. And then we'll take a couple of weeks or like a month to get through the edits. Each screenshot Anton did is now a separate file that I need to download and make sure that it's going to be that's on me. It's fine.
Why do they do it like this?
But anyway, thank you.
Did they at least tell you when it starts?
I can actually align it semi-automatically. Not to the frame level, but like
something.
Roughly.
That's something.
And in a couple of weeks it should be out. Gentlemen, please stay in the call so that I make sure that all the footage is uploaded. So thank you, everybody.
Oh, yes.